Yes. So welcome everybody to Pisa. You've received folders which contain a very important information. If you want to have lunch and dinner at the Scuola Normale cafeteria, I suppose you find codes, 2 codes, which give you access to the cafeteria, and probably you don't know where it is, so maybe you can follow me at 12:30 for the first time. You will see, because you have to learn the various buildings depending on Scuola Normale Superiore. You are here in one of the buildings, Castelletto, with this nice auditorium. The Centro dei Giorgi, who is hosting this conference, is another building on the big square Piazza dei Cavalieri, and the cafeteria is still in another building. So we'll see that later. But please, before going to lunch, look at your virtual badge, these codes in your folder. Each of you has been assigned an office in Palazzo Puteano, the building of Centro dei Giorgi. And this might be convenient to have discussions, interactions. In this building there are also rooms which are very nice if you want to have discussions with several people. You've seen that the timetable, the schedule is quite light, and we hope there will be some interactions between us. And you will see this Puteano is a very nice building with many other spaces to be used for discussions. Feel free to explore. So lunches and dinners in cafeteria if you wish, except tomorrow evening there will be the social dinner in a different place, in the restaurant, to which you are all invited. That's all for the opening words. So we start our morning session with Ricardo as our chairman.
Okay. So first speaker of the morning will be Frédéric Fauvet, giving us a talk on resurgent monomials and saddle nodes.
Yeah, okay now? Thanks. Resurgence is appearing in many contexts, in particular in many contexts in physics, and I'm not proficient for this. I'm very much interested, but my original field of expertise is singularities of dynamical systems. So I will just start from singularities of analytic dynamical systems, and we will focus on one particular type of singularity, the so-called saddle node. I will explain everything. And so the idea is to introduce some general concepts on resurgence and alien calculus, alien derivations, and see how they work, put them to work in a very precise example of singularity of dynamical systems. So in order not to go into some very general information, keep focused. Okay, let's say singularities of analytic dynamical systems are special points, either for differential equations or dynamical system with discrete times. We'll hear a little about that, I guess, these aspects of things with Maya's talks later in the week. And okay, there are singularities, there are which are called irregular, and they are the ones for which divergent series appear. But they don't appear alone. And in the same time as this divergent series appear, there are some exponentials. If x is near to 0, and I will keep the letters later on, x will be a variable which will always be close to 0. Well, there are some exponentials, and exponential of constant over x, exponential of a constant over x squared, etc. And so the two things work at the same time. Divergent series with a certain pattern of growth of the coefficients together with exponentials. And one very basic remark from the start. For example, if you just look at the singularity of a linear differential equation and singularity at 0, you can have a basis of solutions involving some exponential and divergent series. And the presence of exponentials of this type, alpha over x, instantly shows you that the situation is polarized. When you want to give a meaning, an analytic meaning to the divergent series, you are obliged by the form of the formal solutions, the presence of the exponential, to go into certain directions. Because these exponentials, if x is a complex number, have a very different behavior according to the real value of alpha over x. It can be exploding or going very fast to 0. So this is a very, very basic remark. I'm sorry, by the way, I will give a number of basic remarks. Maybe you will consider they are too well, easy things, but I think it's important, according to me, to start from the start. And by the way, we have coordinated with David, so my talk, to a certain extent, is an introduction to maybe more specialized and maybe more interesting things that David will have to say later on. Okay, so now the divergent series that appear for this irregular singularities, and even for linear differential equation with polynomial coefficients, for example, they might be divergent, but the divergence has a certain, there is a certain control over it. They display Gevrey growth. Gevrey is a French mathematician from the beginning of the 20th century. So we have this type of inequalities. And for the situations we'll be dealing on in the rest of my talk, S will be equal to 1, which is a standard situation for many equations which have been studied in math, but also in the physics literature recently. Okay, now, when we have to deal with this divergent series, there is a suitable variable which will be close to infinity, and I will keep the letter z. And when we express this formal series in the variable z and perform the Borel transform, well, what we get is a convergent series. If the an here, if the an have a Gevrey 1 growth, then the Borel transform in the variable z, let's say in this case z is 1 over x, is a convergent germ. And the whole point is to extend this germ and, if possible, perform a Laplace transform and to get sectorial solutions. So let me draw the first thing here. Let's say you all know all this, I'm sure, but it's just to fix the notations, which will be important for a little bit more sophisticated things later on. Okay, so we have a formal series of the type which is written here, in decreasing in powers of z minus 1. Okay, and we perform a Borel transform, and we get a function, and we'll keep the variable zeta So what happens here is the so-called Borel plane. We get function, germs, in the zeta variable, and then the whole point is to perform the analytic continuation of these germs, and in many situations, it will be possible along most of the directions. You remember what I said? It's polarized. We have to go into to look into given directions. And in certain directions, it will be possible to perform a Laplace transform, L theta. Here, the theta means that, okay, this is the Borel plane, and I perform this Laplace transform here on the direction D, which has the angle theta with the horizontal axis. And this way what we get is a function, phi of z. And by the composition of the two operation, we get a sum. And so in the z plane, theta, here is minus theta, we get functions in half planes of this type. This is in the z variable. And last thing I will write here is in the x variable, what we get is a sectorial sum. Okay? So we have this way obtain sectorial sums, and then we can move the direction of summation, and these sums, most of the time, they fit together. But if we cross certain singular directions, well, on the overlap of the two sectors, these sums might be different. This is Stokes' phenomenon. Okay. Now, this is the general process of Borel-Laplace summation. There is no resurgent functions. There is no alien calculus in all this. And there are many ways to deal with the Stokes phenomenon without going into the resurgence business. But in my opinion, the resurgent function theory is the most precise and most and richest way to cope with this question. So what happens? What is resurgence? Well, in practice, the functions that we obtain this way by our Borel transform, they can be analytically continued, and then analytic continuation have isolated singularities. And the whole process of resurgence is to analyze these isolated singularities, and with the help of so-called alien calculus, alien operators, which I will now introduce. Next thing to say is that this Borel transform, it might look, of course, at first sight a bit brutal. We just, okay, we have factorial growth, we divide by factorial, so we get geometric series, and it converges. But the point is that it has good algebraic properties. This is a morphism of differential algebra, and this one also is a morphism of a differential algebra. Where are the operation? Here it's the ordinary product. Well, I don't write the sum. Here it's the product formal series, product of analytic functions, and here there is a convolution, and the convolution of two functions is S is close to 0 in the Borel plane. Okay, and here there is a D, which is D over dz, acting in formal series. By the way, it increases the valuation. And here it's also d over dz, but acting on functions which are defined on half planes in the z variable, z near infinity. Here, the derivation is multiplication by minus sigma, by minus zeta, sorry. Okay, so this is a derivation. Of course, it's not a derivation with regards to the ordinary product of functions in the Borel plane. It's a derivation with respect to the convolution product. Okay, so that makes the whole process valuable, is that if we have a function here which is a solution of some differential equation, as both morphisms respect the operations, the structures of differential algebra, automatically what we get by composing the two things will be a solution of the differential equation, but it will be a holomorphic solution of the differential equation. That's what makes the process of Borel-Laplace summation valuable. It respects the structures of differential algebras. Okay. Then, as I said, I want to go into one specific example, highly non-trivial, but just one, and we will expose, most of the features with this example in mind. So there is one slide that summarizes the situation. So what we are interested in is the singularities of the saddle node sides. What does it make, saddle nodes? Well, saddle node means we consider this equation extremely simple, of course. But you're interested to this equation near infinity. The exponential function is very regular near zero, but in infinity, there is a dissymmetry, as I said before, according to the sign of the positive, of the real value, of the real part of z. Okay? So it is called a saddle node, because if I draw the curves, of course, the real curves, here, you have the exponential here, but exponential 1 over x. And here, on the other side, you have these exponentials, and you have a constant of integration. So you have the solution, the singular foliation, which looks like this. So you have a saddle-type behavior on the right, and a node-type behavior on the left. And this is a first example of irregular singularities, this hence the name. And they are a generalized version of the saddle nodes. The point is to understand the exact, to try to get a complete understanding of this saddle node. So the general process, since Poincaré at least, is to try to transform it into a normal form. In terms of vector fields, now, if we can, this equation will correspond, okay. What will give this solution? There will be the integral curves of this vector field. X and Y are near, now I'm lost. No? You had seen everything? Yeah. Okay. Okay, we're interested in the, this equations correspond in terms of two-dimensional autonomous vector field to this form. And now we'll consider this general situation. So we'll give ourselves a perturbation. X is x norm, this one, plus a nonlinear perturbation. And the aim is to completely understand these vector fields. And as a fact, this problem has been solved at the same time by Écalle with his theory of resurgent functions, Martin and Ramis with a different study of Stokes phenomenon. I will not go into this. That goes back to the late 70s. And it is a very difficult problem because it involves a nonlinear Stokes phenomenon. We'll see it in a minute. Okay, so it's just a statement of results and nothing about the proofs here, of course. When we give some normalized, fix some particular class of vector fields here, this vector field is formally conjugate to x norm, meaning that you have a change of coordinates, which x, y sends to x nor, y nor, to normal coordinates, such that in the new coordinates, x is transformed into these normal forms. General scheme, going into normal forms. Okay. Moreover, it can be shown that this normalizing transformation can be fibered. I mean, meaning that it will leave x fixed. It's possible to find a function, a formal series in the two variable x and y, such that a transformation like this sends x to x norm. Moreover, if we impose that this is tangent to identity, the second here, the linear part here is just y, it's unique. And here comes the divergence. The divergence series arrived here is this transformation can be expanded with formal series in X, and all the series which will be appearing, will have a Jouvre 1 growth for their coefficients. But moreover, they can be summable, and remember, I said in certain situations we can continue and get a sum by Laplace transform. So we have to prove that Laplace transform is possible, that you are allowed to do it, so you have exponential growth for this analytic continuation. So it will be possible in any direction except two. There will be two singular directions, R, positive real and negative reals. And so what happens is that for this, saddle nodes. In the Borel plane, you can perform, you get something which will have all the normalizing, the series involved will have a non-zero radius of convergence, actually a radius 1, and you can continue along any directions except that one and that one. What is Stokes' phenomenon is just a comparison of a sum, like if you focus, for example, in this direction, if you resum in slightly above by choosing a Laplace transform with a direction which is slightly above the positive real axis and slightly under, and you compare on the overlap of sectors, there is a large overlap. Both sectors are for opening pi, so if you're very close here, there are very large overlap. Well, there is a Stokes diffeomorphism that sends the family of solution. Remember, it depends on there is a constant of integration here, sigma, and you will see this sigma again in David's talk. Okay, here, family of solution for the elementary case, constant of integration. Okay, and then I will keep this the same letter. So we are interested in all the solution of x, and through the normalizing process, we get, as we know the complete set of solution of the normal forms, we will get the complete form of the solutions of the differential equation, which corresponds to the field X we're interested in. Okay, and so we have to cope with the Stokes transformation, which here compare for the positive real axis, the summation slightly above, slightly under the real axis, and same thing in the other direction. Actually, the situation is dissymmetric. In one direction, the negative direction, the Stokes diffeomorphism amounts to a translation of the constant of integration. When you compare the sum here by a direction of summation here and there, on the overlap of the sectors, it amounts to a transformation by a translation on the constant of integration here. But on the other direction, it's much more difficult. It will amount to another transformation of the constant of information. There is a permutation of the set of solution. Remember, once again, we're interested in all the solution of these equations. And, well, the transformation goes like this. It sends sigma to sigma plus h2 sigma squared, etc. There's an infinite family of coefficients, so it's analytic transformation. So it's the Stokes diffeomorphism, which has noted H here, belongs to the set of analytic diffeomorphisms which are tangent to identity. And it's a very hard result that this gives the moduli space. I mean, if you are interested in classifying all of these vector fields with these normalizing conditions, which are conjugated to these normal forms, well, the moduli space is huge. It's of infinite dimensions. It's C times the set of diffeos tangent to identity. C corresponding to this constant C, and this side corresponding to the Stokes diffeo here, H. It's a very hard result by Martin and Ramis, and obtained at the same time by Ekal, with, well, indications of the proofs by Ekal in the late 70s, early 80s. Okay? Now, let us go here, on time, I think. Let us go to resurgent functions. Okay, so what are resurgent functions? First approach, they are functions of one complex variable with isolated singularities. First, there is no Borel transform, no Borel Laplace. It's just a chapter of the theory of functions of one complex variable, nothing more. Functions of one complex variable with isolated singularities. Well, what do we mean by isolated singularities? Let us be more precise. It means that we will consider a set of analytic germs at the origin. So the drawing here will be in the zeta plane. So there is a disk of convergence, and we ask that it can be continued, such a germ we are interested in a set of calligraphic E of germs, which can be continued along, let's say, any broken line like this. It can have self-crossing. It can be continued by the process of analytic continuation, except for a possible finite number of singularities here. Perhaps we'll meet one singularity here, one singularity there. Okay. But in this case, what we ask, this is in the definition of the set we will be working in, is that we will be able to continue by circumventing the singularities, going this way or that way, at least. Well, there are various algebras of functions, but at least the basic thing is that, you know, with here a slight overlap of the two continuation by the right or by the left. We don't want a barrier of singularities here, a natural boundary somewhere, just isolated. By the way, also, there are some generalized version of resurgence in Ekal's paper, but I will definitely not go into this. So that's what we want. Isolated singularities. Now, it's easy to see that this set of germs has a natural structure of vector space. But then, now, remember what we had spoken from the start from the Borel transform. There is a convolution, and then we can consider just algebraic function, analytic function theory on this set, this convolution product. Well, it's a highly non-trivial fact that this set is stable by this convolution product. And there are, well, it was stated, and with a number of techniques for the proofs by Eka a long time ago. And it has been done in details in various situations of increasing generality by David and co-authors quite recently, as I guess most of you already know. So now we don't have we have more than a space, we have an algebra of function with isolated singularities. And the point is that there are operators in such a space which measure the singularity of omega of the analytic continuation of a path from the origin to omega. Let's say we have here a singularity. We have here, let's say, a singularity, let's say here at the end of this path. Okay? So they will have operators, which a priori, of course that's the point, will very much depend upon the path we had followed in the process of analytic continuation to reach the point omega. Now, as we will see now, I will go and be more specific, more precise in the next slide, but one maybe important thing to keep in mind about resurgent functions is the definition is not so easy, this is the first step, is that resurgent functions, they are not functions. There are classes and functions of functions in general, and stricto sensu, they are not resurgent. So resurgent functions are not functions, and are not resurgent makes life a bit difficult. They are resurgent in the applications, in many physical situations, and now there's been an explosion of results, and in many situations I know, of course, in classification of analytic dynamical systems. Is that okay now? It's just basic, remarks, but I think it's necessary to come to that. Okay, now, we'll now define the alien derivators. Maybe when you look in Ekal's papers, you see an intricate combinatorics, and maybe we'll go into this later in the discussions. It's not the point. The combinatorics is very smart, but it's just combinatorics. The main point is the process of analytic continuation, to understand the analysis, and the difficulties are really here, to prove that the things you are really working in the spaces of functions where the operators that you want to define make sense, and this demands a lot of efforts to prove this precisely. This is in particular the things that David has brilliantly done in the last years. Okay, so now, remember, the situation is polarized. First situation, we have a singularity here for the analytic continuation. Maybe there are other singularities, so if we take a complicated path, we'll reach the singularity, and another complicated path to reach this point in the complex plane. Of course, the functions themselves will live in Riemann surfaces above the complex planes. But if you follow a path here and reach the point, you will get different behaviors according to the path you choose. But there is a simple one, and it's natural, once again, it's polarized. It's just a straight line. If you are able to follow the analytic continuation to a point omega, then you can bluntly define an operator this way. Delta omega of phi of zeta is phi omega of omega plus zeta. What does it mean? What is phi omega? Phi omega is just a result of the analytic continuation near omega. So it's a function which is defined not in a disk centered at omega, but on the universal cover of a pointed disk center of omega. You remember what we had required? That we could go this way and around, most of the time circling an infinite number of times. Okay, there are technical here situations of various increasing difficulty, but to make it simple, let's suppose that you have functions which you can continue on the universal cover of a pointed disk. It's essential, it's not a disk. You have a singularity, don't expect it to be regular, of course. So phi omega is the function which is defined on the universal cover of a pointed disk centered at omega. Now you do two things to define this operation. You extract the singularity. What do I mean? I take this analytic continuation and I translate the variable to the origin. You see the translation is here. Here I have a function phi omega which is defined close to omega in a sense which I've indicated before, and then we get a function which is close, defined for zeta near 0. But beware, near 0 and a universal cover of a small pointed disk at 0. It's a priori, it's singular at 0. And we want to define that it is a singularity, so we consider this moduli the regular functions. So this is our first example of an alien operators. It extracts, It extracts the singularity here with this function phi omega. We translate the variable to the origin and we mod out the regular germs. So we have a singularity. Okay, so we have associated, and that's the point, we have associated to a given regular germ a class of singular functions. Well, then there is something which is a bit inconvenient because we started from a convergent germ and then we got a singular the class of a singular germ. We would like to iterate this. We had defined an operator which starts with my space calligraphic E and which goes to a quotient space of singular germs. So it's very inconvenient because we would like to start from this germ and then explore other singularities, but starting from here. So there is something dissymmetric. Well, there is a way out of this. It's just that you can consider a regular germ, the regular germ you started from itself, you can see it as a singularity. There is the same amount of information in this regular functions. You remember phi was a regular germ at the origin. There's the same amount of information as in that one. You can say, oh, this germ is the singularity at the origin of this function here, the class of these functions, okay? And so another piece of information now and definition of our real space, a space of resurgent functions will be a set of classes, moduli regular germs, of functions such as phi hat as isolated singularities. What is phi hat? It is the variation, this is terminology going back to Deligne, but notation are those of Écal. It's just you take the germ of the origin and you consider the same germ. Remember, it's defined up now on the universal cover of a small disk pointed at the origin. So we go for the argument minus 2 pi I, and we consider the value here. You make the difference. Of course, if you started from this thing and you perform this operation, what you get is exactly phi. Of course, the 2 pi I is here to get exactly the good coefficient. And so this thing here corresponds to the function phi here. So for this type of singularities, remember, this type of singularities encode regular germs. This function here is exactly the function phi. Okay? Now, what we want, and this is definition, we will call resurgent function, the set of classes. So that's this thing here as isolated singularities. And now that's okay. We have operators and we can iterate because we started from a set of classes and we arrive to a set of classes with the same properties. Okay? Now, this is what I've done here is in the case when we just meet, it's the first singularity we meet. And what will happen when we have a number of singularities in the same direction? Once again, it's important. We want a definition that fits the general pattern. It's polarized. We look into directions. If there is a singularity, if this is the first one, no ambiguity, we have done everything. We'll see in a minute what happens if there are a finite number of singularities. Okay, now, this is an algebra, and we have to extend the convolution we had defined before, and for the germs which are regular at the origin, the extended definition of convolution, which I will not give here, extends the convolution most of us are already used to. Okay, and okay, now terminology. One of these phi check is called the major of phi, and phi hat is called the minor. So the space of resurgent function is a set of class such that the minor can be continued with isolated singularities. Okay? And now we are ready to iterate the constructions. We have a space of endomorphisms. Okay, half hour, so I think it's okay. A little bit, I mean more than just half hour. Okay. Now, I said just a minute ago that this is what happens if this is the first singularity we meet in this direction. What happens if there are a number of singularities? By the very definition from the start, we'll have a finite number of them. And there is maybe a first one, etc. And so you perform the same process. We are polarized, so you don't go around in the other direction. You follow very closely this direction you are watching, but you have to make it precise the way you circumvent the singularities which are in between the origin and omega. Okay, and in the process, there is a finite numbers of analytic continuations, so you can hope that there is a suitable average, finite, once again, it's a finite number of singularities. So in this direction, you have a finite number of analytic continuations, and you can hope that if you finely tune coefficients for these finite sums, give weights, you will get operators which will measure the singularity here, and which will have good algebraic properties. And it was one of the first major discoveries of Écart, and almost 40 years ago, 40 years ago, is that, well, there are families of operators with coefficients, and there are many families of them, and I will not go into this right now, maybe later in the discussion, such that the operators are derivations. Derivation with respect to the convolution product. Now, all this business is analytic continuation. It's in the Borel plane. It doesn't make sense at the level of formal series. But now, if we have formal series which are obtained as Borel transform, if we have, functions phi of zeta which are obtained through Borel transform of formal series which are solutions of a problem we're interested in, the classification of an irregular singularity or problems coming for physics, etc. Well, we can pull back just by Borel, inverse Borel, these operators. And now I introduce another definition. Blackboard bold delta omega is defined like this. The ancient terminology of Écart over notation, which of course can keep is delta omega dot. Another notation for this thing here. Another notation would be to call it delta omega like this with a dot above. And so this thing have the advantage of commuting with derivation. So they are Galoisian in other terms. Okay, now this is important to keep in mind because there are always three aspects to resurgent functions. There is the aspect which is, well, we have in mind when we speak about when we work with resurgence is the fact that there are singularities and there are the alien singularities at finite distance and there are alien operators which enable us to analyze and give us numbers that we will see later on in which way we get numbers. And there is also the fact that it is singular at the origin, but the formalism of major and minor takes care of this. And we can extend all these concepts with two formal series, which are not only decreasing series in z minus 1, but also involve powers z to the alpha, or even powers of logarithm, etc., in such a way that the process which I've indicated at first, Borel-Laplace summation, here, is each step a process of that respects the structure of differential algebras. Here, from the start, we had defined, without ambiguity, a Borel transform for series in z minus 1. If I put into the business z to the alpha, or if I put powers of log, I must define correspondingly what are the singular germ of the origins, which can take care of this, and define a Laplace transform accordingly. The Laplace transform here will take care of the singular behavior at the origin in the Borel plane. So instead of integrated among array, we'll have something like that, which takes care of the singular behavior. And this type of drawings you have maybe already seen in a number of papers by Boros and many other people dealing in physics with this type of things. It's in fact integration of a major, and it respects the convolution when we have the adapted definition of convolution. So the formalism is has very wide structure, okay? So, and the last part is the growth of infinity, and this is usually quite technical. And here also, for a number of situations, I refer to David's papers. And by the way, there are also extensions of this concept when there are not only one critical variable z, but several, a finite number of them. It involves the process of acceleration by Ekal, but you will need a number of years to decipher it correctly, because no one has really used it, at least in nonlinear situations. And the fact that these three aspects are crucial. Singularities at finite distance, singularity at the origin, growth of infinity. In the process of acceleration, you will have more completed growth of infinity, and proving that is a difficult business. Okay. Good. Now, let me state the result for the resurgent study of the saddle node. Saddle node, you remember, it was vector field dimension 2. Now it's convenient for resurgent, for stating the result with, in the language of resurgent, to reformulate it as an equation, a non-linear equation in a variable phi, y, and you remember the function phi from the start, which was the second component of the change of coordinates. Well, it corresponds to the general solution of this equation, nonlinear, okay? And it can be expanded this way. You remember we have seen this before, the exponential 1 over x, which were the exponential in z. And we have an infinite number of formal series, and it's a proposition, it's a theorem. It's actually very hard to prove. It's a serious analytic business to do. The phi k are all resurgent, meaning they are Gevrey-1, the Borel transform have singularities. And where are the singularities? You remember this, I've drawn the two singular directions for the saddle node. You remember before? The singular direction for the saddle node? There was the positive real and the negative real. And I said, well, the series involved will have a radius of convergence of always 1, and the singularities will be here at the non-zero integers. Okay, and what type of singularities are these? Do we get for the Borel transform of all the series? We get simple poles and logarithmic singularities. Simple poles, coefficients like this, and logarithmic singularities, meaning where A is analytic near the origin. Okay, so it's a proof, and it has to be proved. It's a theorem, and it's not a proof. And it has been done in great details notably in a reference by David, which I will mention in, I think it's the next slide. Okay, so they are resurgent. Now that we know that they are resurgent, and that we know that we have at hand these alien operators to analyze the singularities, we can apply these alien operators. And this is, what do we get? Well, these alien operators, when we let them act on phi, well, in fact, it will act on these things it'll act trivially in this spot. When it acts on this thing, it acts as an operator, an ordinary differential operator, but an operation in d over d sigma, which is the parameter of the family of solutions. So this is our first example of the bridge equation. It's a bridge between alien differential calculus, measurement of singularity, and ordinary differential operators. And also, moreover, the differential operators here are very simple. There are questions of homogeneity, and so there is a sigma to the n plus 1, and there is a coefficient an. But what happens is that the numbers are invariant. Invariant with respect to what? To the change of analytic coordinates. And this family characterizes the class of the equation. Now, the bridge equation, which is written here in a very concise form, Ekal lies ultra-concise formulas, encodes a huge quantity of information. And in fact, it is decoded in this way. It's when you interpret it component-wise, as I said, this here acts in phi, but in fact, it's on the phi k that it acts. It acts non-trivially. And it acts in this way. When we translate this general concise form into this, what happens for the phi k, we have this thing. So we have our first instance, and we'll see another one in a few slides, of resurgence. When you analyze the singularities of phi k, it's resurgent. We analyze its singularities with the help of these alien derivations at the point n. What we see is phi, not phi k itself, but another phi l, phi k minus n. So there is a resurgence, there is this function which appears at the singularity n of the function phi k. So this is the origin of the name resurgence. At the singularity of a function, you see something else which we know reappearing. In some very rare instances, for example, in the classification of analytic diffeos tangent to identity, these are this type of questions that Maya will probably evoke on Friday. It was the seminal questions studied by Ekal. There is a formal series which itself reappears at its singularities, but most of the times it will be a bunch of formal series, for example, for a linear equation, formal series appearing in the basis of solutions. And when you analyze the singularity at the point of one of these formal series in the Borel plane, you'll see another one reappearing. This is exactly what happens here, hence the name resurgence. What's the connection between the Stokes diffeos we had indicated before? It's here. Remember, I said the Stokes data, which characterizes the analytic class of the equation, this is a very hard result, is just two things. A constant, remember, translation over sigma, and a diffeo tangent to identity. This corresponds, in fact, to the same family of data. And how is it? What is the connection? What is the connection? Well, in fact, the Stokes diffeo in the easy direction, that one, translation by a constant, is the exponential of a minus 1 d over z zeta, exponential of translation by a constant. And in the other direction, you take the formal sum of all these operators, and you take the time 1 diffeo, the exponential of this, and this happens to be analytic, and it is exactly this h. It's not trivial, but it's the relation between the family of numbers, infinite family of numbers you get by applying the bridge equation, and the Stokes diffeos, easy direction, translation by a constant, but also, when I say easy, it already yields a treasure of information for a number of situations in physics and also in math, and more difficult direction, that one. Okay, this is the connection between the two approaches, Stokes diffeos and alien calculus. Okay, I think I have 15 minutes. Okay, now, SNAG, what does it do? It's an acronym, it's Singularité non abordable par la géométrie. It's an incredible paper by Ekal. So in English, it has a challenging title, Singularities which are intractable by geometry. I will not go into the details of why this terminology, but Ekal copes with a wide number of problems. He considers in this paper singularities of vector fields, analytic data, in any dimension. and also differs in any dimension around near a singular point. And he considers, let's speak only of vector fields, of the resonance situation. What is a resonance? Well, you suppose that, let's say, the linear part is diagonal with the spectrum, and a resonance is a relation of this type. Saddle node is the first example of saddle node singularity. Saddle node is where you see the spectrum at the origin is 0, 1. You see x, there is no linear term in x and there is a y. So the linear part, there is a resonance with the 0, 1 eigenvalues. Okay, that was the saddle node. So in this paper, it copes with any resonance and also small denominators. Well, quasi-resonance, which you call quasi-resonance, what are the small denominators which appear in celestial mechanics and in many situations and classifications problems and for dynamical system is when these quantities may not be zero, but they can be very small. Then you can get analytic results of analytic classification by imposing some condition of this. The fact that, okay, in this, the lambda I are respectively one to the another, not too well approximated by rationals, so there are a number of conditions, Siegel, Bruno, so it's a very well established theory. Well, in this paper, Ekal copes with the most general situation. And what I have indicated, and I will show in the last slides, is a tiny part of what is contained in this paper. But even if we don't read French, the formulas are, I think, quite readable, and it's valuable, I think, going into this paper, because there are many papers in English by Ekal on his home page, but many info are in this paper and not in other papers. So, okay, and the most relevant reference for what I'm explaining today is the paper by David, who was published in 2009, already, well, 10 years ago, and the preprint was an archive here, okay? Now, what are these resurgent monomials, which are, well, my primary aim in this talk? Well, it's just common sense. Once you know that resurgent functions are not everywhere, but in many places, and once you know that you have at hand an apparatus of alien operators to analyze the singularities in the Borel plane and then understand the Stokes phenomenon if you want to go to functions in complex domains near your singularities, and if you want to understand, to get numbers eventually, all this apparatus of alien operators help you. Now, you can look if there are simple resurgent functions that behave well with respect to these operators. It's just common sense. Just think of the ordinary derivation. Function of one variable x. If you consider this Euler operator, well, the monomials here, simple monomial, one variable, they behave as eigenvalues for this, Euler homogeneous derivations. So they are simple with respect to this derivation. Well, it's common sense. If you have these operators, and you know, and I think all of you, most of you here are convinced that they are important, these operators, then you can look if they are resurgent functions which will behave well with respect to these operators. Well, in fact, there are many operators, and they don't commute in general. So it's not exactly this that you will need. You will need to consider composition of these operators, and so you will need to consider to each family, which Ekal calls a sequence, or word if you prefer, in the letters. Think of the letters of singularities, and keep in mind the saddle node. The letters will be integers, part of the, well, integers. And so what you would like to have is functions, or a family of functions which are as simple as possible, which behave well with respect to the product, which we behave well with respect to the ordinary differential, the derivation, one variable, it's one variable, and also which behave well with respect to the composition of alien operators. It's very common sense. And so, of course, Ekal had thought about that from the start, and he had built since the late 70s many families of these so-called resurgent monomials, because this is the way we'll call them. And now, 10 minutes, I think I'm okay. Now, there is one exercise that I think most of you have done, and certainly everyone should do when coping with resurgence, is that if you take a function such as this one, two singularities, when you singularity here, singularity there, when you compute the convolution product of this thing, you will see a pole at omega 1 plus omega 2. Well, yeah, let's say omega 1 plus omega 2 is here. Okay, function, regular at the origin. One singularity, a pole here at omega 1. They're just a single pole. When you compute the convolution product, first near the origin, and then you extend, well, what you get is logarithmic singularities here and there, and a pole there, but beware, it will depend on the way you reach the singularity. In the star of holomorphic, the residue will be 0, but if you go around, it will depend on the number of times you wind around any singularity, you will get a pole here. So this is an essential thing. Convolution adds singularities. Convolution adds singularities. First thing. Other basic remark, when you're interested in such a problem as the saddle node, you immediately meet, I said, you remember, there are singularities which are single poles and logarithmic. When you do it by hand, you see them appearing by any perturbative method you choose. Then, of course, you have to prove convergence. It's a difficult business. But you see simple poles and then logarithms. Then you say, okay, look, I want to build this family of resurgence monomials. And I want to be able to use them in concrete situations. So I must put into the machine single poles and logarithmic. So the easiest, the most, not easiest, let's say, yes, the most natural in any way, in any sense, the most natural way to do this is that like this. You start with a single pole, you integrate, and then you take into account the fact that you have a singularity at omega 1, and then you add singularities. So see the recurrence relation here. It defines you unambiguously for any sequence here. For any sequence, it defines you a family of functions which will have singularities at omega 1 plus omega 2, omega 1, etc., plus omega r. And they are explicitly constructed. Okay? And so there is this recurrence relation here. Integration is just convolution by 1, where is a minus sign, which is convenient anyway. So in the Borel plane, these things are Borel transform of these equations. So you see, with respect to the ordinary differential, derivation, it's okay. It's not complicated. See, it's very simple relation. What happens when I introduce one piece of notation? This is just formal. We multiply by omega is just the sum. Oh, by the way, sorry for this. The notation of égal. And if we have a sequence here, think of them as singularities. Saddle node, they are integers. We just consider the sum. Okay? Now, you see here, these functions, they behave well with respect to the ordinary derivation. This is simple. This is just an inverse Borel transform of this thing. This is easy. Okay, and I remark that we need a more general version of these with a non-integer power, and through the formalism of minors and majors and minors, we can cope with this. Okay, this is in the paper snag, and we'll really need it in our joint work with Olivier Bouillot. Now, and this will be our second example of resurgence in my talk, is that when it is a proposition, it's non-trivial, is that when you apply an alien derivations on this thing, what do you get? You get a finite sum of these things. So you see a resurgence, because in the, look, at the singularity of this one, at the point omega 0, you see the other functions of the family appearing. You see for other subsequence, okay? And what are these here? They are numbers. So they can be called resurgent coefficients. What does it mean? It means exactly this. I mean, when you apply a delta omega, you measure the singularity of this thing at the point omega 0, you get this finite sum. And of course, in particular, it is 0 if this point here, which indexes, if you're interested at a point which is not a partial sum of these omega i's, well, there will not be any singularity. Okay, so there are many families of resurgent monomials. These functions are the hyper logarithms, which many people are considering also. And I think in many situations when you cope with resurgence, it's most valuable to deal with this. And once again, the best place to learn about this is the reference by David I mentioned a minute ago. So 5 minutes, so I will have to go quite a bit fast for the last two slides. I will skip the work with Olivier Bouillot. Okay, let's go back to the saddle node. We want to build, you see...
I think if you change the grip by using your thumb instead...
Yeah, but... yeah, maybe you're... Yeah, you're... Yeah.
I think it's built like to handle it.
Yeah, okay, let's try. Maybe it's better. You know, it's like my daughters with the cell phones and the thumbs, and I'd use this. Okay, now, well, I'm a bit clumsy here. Let's see. Okay, you remember, we want to normalize. No, I'll train at home, but for the moment, yeah. Okay. We want to change, remember, we want to build a change of coordinates. And now there is one thing which is everywhere in ECAL, and I wanted to indicate it, even if it's briefly in the last 3 minutes, is that because if you go to ECAL's paper, you have to keep in mind in all these situations, it works not only not with changes of variables, but with automorphisms of substitution. What does it mean? Well, if you have an observable f, a function, you see, which belongs to some subalgebra of formal series in x and y, for example, C of x and y itself, then you can, if you have an invertible formal, let's say, transformation, you can consider a priori this big theta. Well, if this small theta is bijective here, then this thing here will be an isomorphism in this, acting on this, let's say, this algebra here. And so, as you will see in a minute, we will transform an equation which is a nonlinear equation in a big theta, in a small theta, in a linear equation, but in a much larger space, but for which we have many more operations at hand. And ECAL is very, has developed a number of constructions of this. Now, how we start the business, you see, x, normal form, plus a perturbation. Perturbation, derivation, one variable with functions here which are analytic. This is the data. We take these here as input. I'm simplifying a little bit here, but we take these as input and we construct differential operators. It's not alien. It comes from the data. It's analytic. So we have very simple ordinary differential operators. We take them as bricks. That's our data. And we take this as inputs, and we construct operators of this type. And now we will try, and this is an ansatz. We try to build this automorphism here by an infinite sub of this type. And of course, there will be some resurgence in the picture. So we would expect this thing not to be complex coefficients, but resurgent functions. At this point, and one last slide, and after the conclusion, reminder, and even if it's elementary, an infinite sum of ordinary differential operators, it can be an algebra automorphism. It's just think of Taylor formulas. F of z plus 1 is this. So you can say that f of z plus 1 is the result of this infinite sum of ordinary differential operators acting of the function f. But then the transformation which sends f to g, okay? F of z sends g of z is f of z plus 1. This is, of course, an automorphism. So you have obtained this automorphism, the fact that sending f to g, as an infinite sum of ordinary differential operators. So, and then 1 minute to for the last slide, and then conclusion. I'll jump to the conclusion. Okay. And so the ansatz is we'll build the object we are looking at, this one here, as an infinite sum of that one, keeping in mind that if we have good symmetry properties on the coefficient, well, we'll get an automorphism. And that's the way it's done. Theorem, if we take the resurgent monomials, the one you have seen before, you take as input the b omegas, then you have this commutation relation which corresponds at the level of this space, big space, and the morphism of C of x, y, to the fact that the small theta will give a change of coordinates. That change sends x to this normal form. Okay? Now, theta is resurgent. What does it mean? It means that it's an endomorphism of the subalgebra of endomorphism of a subalgebra of C of x when we have series in x which are resurgent with singularities in Z. It satisfies this commutation relation. And in fact, here we have operators, which are the one we saw before. I'm obliged to be very fast here, but you remember the bridge equation. It was on the trans series, this infinite sub involving exponentials. When you take this thing, big theta, we go back to the small theta, which corresponds, this change of variable, and we pull back by plugging in the general solution of the normal form, we get a trend series, and we see these operators acting like in the bridge equation we had seen before. But the last theorem is the last point, is very important, is that you have explicit formulas involving the numbers V. So that was the whole point of Écale. He has an explicit effective access to Stokes' diffeomorphism. Remember, moduli space is huge. If you just look at the positive real direction, you are working in a space of diffeos of tangent to identity. It can be put, given a structure of analytic variety of infinite dimension. Okay, you are working in a big space. For the use of alien derivation, you will cut the difficulty in pieces by just going into any isolated singularities. Instead of going over the whole direction, you focus on one, focus on two, focus on three. You extract with this business of resurgence monomials and this constant here. You extract what happens at each singularity. Yeah, and you have an explicit formula of this type for this coefficient of the bridge equation. Okay, now I'm concluding. Okay, I'll skip the work with Olivier Bouillot. And conclusion, okay. So, alien derivation working together with resurgence monomials can be, as a general principle, very efficient to tackle some question of classifications. Speaking of what I know a little bit, mathematics, this part of mathematics. And I mentioned that the formalism can deal with small denominators. Then instead of sequences like this, you will need trees decorated by these numbers. Okay, and I point to two recent references. Well, the seminal reference is Écale snag, and the whole technique is due to Écale, of course, and all the schemes for the proofs, etc. But there are papers by Frédéric Menou from Orsay and myself in the Annales scientifiques de l'École normale supérieure, 2017, and another paper which is in press, maybe just out, Bulletin de la Société mathématique de France, with Frédéric Menou and David, coping with this, explaining, I think we do it clearly, how these trees can be used in these situations. But the point is that more generally, when you are dealing with resurgent functions in a situation, physics, modular problem, etc., what it might be a good idea is to try to express the quantities you work with resurgent monomials. And I'm concluding here. Thank you.
I just wanted to see.
You want to see?
Yeah.
Well, with Olivier, we used here also a small part of what is of the techniques which are in SNAG, but to deal with these situations. So saddle node singularities are here in the Borel plane. Okay, two singular directions. What is the next level of difficulty in a nonlinear situation is that when you have a two-dimensional lattice of singularities, for example, the Gaussian integers. And then it's tricky. It's tricky because there are an infinite number of singular directions. Any direction with a rational slope is singular. So if you take a slope which is irrational with an angle which is, an irrational slope, then you can go in between the singularities, but you have to perform some careful estimates close to the singularities and when going to infinity. But it fits in the general formalism. And by the way, that's why I'd written it this way. It's exactly the same statement, so, except that you put as input, you put resurgence monomials with singularities in this set instead of that one. But the general formalism is exactly the same. But there are many technical complications, and the simplest situation is what I mentioned here. Dimension 3, vector field, linear part, 1, I, minus 1, minus I. So it's resonant. Okay? And in fact, the component of the normalizing transformations will have singularities. And I don't see how classical Stokes analysis in sectors can cope with these things up to the analytic classification in this situation, whereas Ekal's technology works. Then the next one is just to make precise the class of vector fields we were studying, but once again, it's the techniques and the methods are all contained in Ekal with a very concise indications of proofs in this fantastic paper, Snag. Okay.
Question?
You mentioned this proposition 1 in which you construct analytic or change of or formal change of coordinates for saddle node. So I was wondering, you mentioned it was Gevrey 1 in. So there are a sequence of series.
Yes,
Z,
with
which
the
are Gevrey 1.
Yes.
And what is the nature in exponentials? So how? So you have a Tron series.
Yes, there's a Tron series with exponential of k over x.
Yes.
And all the formal series are Gevrey 1, and there are some also uniform estimates on the growth of the coefficients of all the series. I mean, each of the series is Gevrey 1, but you can resum all the series at the same time and get solutions in domains which are in sectors in Z, and with which is analytic in the Z sigma constant of integration. So, but what? Maybe I misunderstood.
No, but the series then you have like two levels. One is exponential, and one is exponential of Z and Z.
Yes.
And then you have some series in Z, and what happens with series in exponentials?
Yeah. I said what you get eventually. Yes, maybe you get a very thin domain here. For in this direction, Stokes, you have a very large domain. Well, okay. So in fact the variable, okay. Okay, you have to keep this small. So that's why you have a very thin domain, but non-empty domain, on which you can see the Stokes phenomenon. The exponential are exploding. Okay, this is the bad direction. But if you work in domain like this, when you impose not only sigma small, but sigma, the modulo of sigma out is Z small, then you have Z large here, but a domain of this time very thin around the real axis, but not empty. Okay. So the Stokes phenomenon is accessible, can be seen not for in domain of this type.
Thank you.
Is it? Yeah.
All right, so let's have a, let's say, 20-minute coffee break.
Okay.
Let's thank the speaker before that.
Thank you.
Put your, it's right there.
Okay. Yes. Maybe this is not needed right now.
Yeah.
Yeah. Okay. Can you hear me?
One
Yeah.
on the pockets. In the pockets.
Okay. Thank you.
Pay attention to the mobile phone.
The mobile
have it in
phone over there.
No, it's okay. It's okay.
Over there.
The problem is the mobile phone is in the pocket.
No. I remember now.
Okay, so let's keep going. And the next speaker will be David Sauzin, who's going to tell us about co-equational or parametric resurgence.
Thank you, Ricardo. So, yes, it's an invitation to parametric resurgence. Parametric resurgence. Whereas the previous talk was about equational resurgence. So we are going from equational to parametric, so which is sometimes called co-equational because it is in a loose sense dual to equational resurgence. And my aim is to try to be as pedagogical as possible and not to give any new result, rather to give an introduction to certain features of that parametric resurgence following two old preprints by Jean Écal. This is one of them. So we are following Jean Écal. There is a preprint in 84 and some part of it is repeated in 92. And in fact, this is an ongoing project with Ines Aniceto, Frédéric Fauvet, and Ricardo Schiappa. So we are trying to revisit this work by Écal, to understand it, to translate it, to provide proofs, and hopefully to get new applications in mathematical physics. So we will deal with a case study in dynamical systems. So I'm more a mathematician, more of an analyst, and more in dynamical systems. So we will consider, for the sake of simplicity and the exposition, a class, so it's a case study, a class of nonlinear ODEs. So dy over dz is y plus a of z and y. So these equations you have already seen in the previous talk. So y is the unknown function, z is the independent variable, so it's near infinity. And this means that we are dealing with a scalar, nonlinear first order ODE, non-autonomous. And so this is supposed to be holomorphic at infinity. So let me put 1 over z here and y. So we are trying to find small solutions of that equation. And this is what Écal suggested to understand the special features, the phenomenology behind parametric versus equational resurgence. If you want parametric resurgence, you add here a parameter. So let me call x. So x is a non-zero complex parameter. It will be large, close to infinity itself. So maybe I should spend 5 minutes to tell you the motivation for that kind of equations, apart from expositional purposes. In fact, Écal was motivated by exact WKB analysis. So let me say motivation, exact WKB. So what do I mean? If you study the one-dimensional stationary Schrödinger equation with a polynomial potential, say, so usually there is h bar square here, so let me put x square. So this x will be 1 over the Planck constant, or the reduced one. And so this W is potential minus energy. Let's say it's a polynomial. Polynomial is a meromorphic function on the Riemann sphere. Maybe you want to consider more general meromorphic functions. Maybe you want to consider different Riemann surfaces. So you can take a meromorphic function on a compact connected Riemann surface, for instance. Let me stick to this. I won't give too technical details anyway. So how do you handle this equation via WKB? Probably many of you know that. You say, okay, let's look for a solution in the form exponential of the primitive of something. Let me call S this something, a kind of action. And then you get this differential equation, first order, Riccati, so nonlinear, S square, and this is the same W, and this is our large parameter, 1 over h bar. So it's clear that if you look for asymptotic solutions, if you look for a power series in powers of h bar, so you start with x square root of W, and then so this is large, and then you add smaller corrections. It's not difficult to compute the smaller correction. I mean, you have this x square root of W. The next term, if I'm not mistaken, is minus 1/4 logarithmic derivative of W. And then, so this is constant in x. And then you have the rest, which will be order 1 over x. And in fact, you can compute a unique sequence of coefficients depending on q, unique up to the choice of the square root here. And so you put that here, you have the choice of the constant of integration, you get your family of, your 2-parameter family of general solutions for the linear equation over there. So this is the trick. So you see that this integral of square root of W plays a special role. The primitive, a primitive of this square root of the polynomial plays a special role. We will use that as the new variable z. So this z here is obtained by this change of variable. And this y is obtained by a change of unknown, something like t, this t. So you see the small part of the formal expansion. There is a coefficient I don't remember, and then, well, it's a Riccati equation. So Riccati equations are very compatible with linear fractionals. So I think if you do this, then you recover that kind of equation. So let me write it here. You recover with these. So from Schrödinger, you go to Riccati, you change variable, you change unknown, and you get dy over dz is xy plus, I think it's h minus hy square, where h is q second of z divided by 2q prime of z. So because this is z as a function of q, so correspondingly you have q as a function of z. And if you are dealing with a polynomial, say, so I said I'm working at infinity in the z variable, so when q is large, this polynomial is, let's say, q to the n plus lower order terms, then this Q of Z is it's something, a coefficient times Z to the 2 over n plus 2. So the change of variable induces this ramification at infinity, but more importantly, the periods of your hyperelliptic function will play a role. So this, for instance, this guy here, it's you can check that these coefficients here are of that form. In that problem, maybe 2 over n plus 2. Yes, so you see it's a particular case of that equation. So you can expand here this A. This A is A0 of Z plus A1 of ZY plus A2 of ZY square plus etc. in the general case. And in this particular case, you have the Riccati case with A0, A2, and nothing else. And it's almost the same, except that here I was supposing holomorphic in 1 over Z. In fact, for WKB with a potential polynomial potential, it would be holomorphic in that variable, but this is immaterial. So, in fact, in the rest of the talk, I will deal with that situation motivated by, let's say, exact WKB. So we have changed the unknown function, but above all, we have changed the independent variable. This means that we lose a lot of geometry when we do that. So in the variable Z, you must be aware that if you think in geometric terms, you see this integral of square root of W, this is the natural parameter associated with W of Q dq square, viewed as a quadratic differential. So it's a geometric object, it's a certain kind of tensor field. It's not a vector field, it's not a one form, it's a quadratic differential. And when you have a quadratic differential on a Riemann surface, you have at a regular point, that is not a zero nor not a pole, you have this well-defined natural parameter, well-defined up to addition of a constant. And there is an interesting geometry for the quadratic foliation if you think of the horizontal foliation, which means in the Z variable you think of the foliation by horizontal lines. This corresponds to a foliation here. Let me say something like that. Something like that. I don't know. Typically something like that. A singular foliation in the Q variable. So this would be the image of the horizontal foliation by the change of variable. And the horizontal foliation is a particular case of foliation by geodesics. I mean, you can have geodesics of different angles. And so these are the horizontal geodesics corresponding to a certain Riemannian metric induced by the quadratic differential. So here you see that there is an interesting geometry. These are simple zeros of W, typically called turning points in WKB theory. We don't see them here. But what happens in the Z variable is that we are holomorphic near infinity, but in the large there are singular points. I mean, you cannot expect the coefficients here to be entire functions of Z. So you will hit singular points corresponding, induced by the zeros or the periods of the hyperelliptic Riemann surface associated with when you take the double cover of the punctured plane, for instance. So in the rest of the talk, we will do analysis, local analysis for Z close to infinity. So there is not much geometry because it has disappeared in this change of variable. But ultimately, it should be desirable to return to the original variable and to. We are not enemies of geometry, despite the provocative title that we heard in the previous talk.
correspond to taking an infinite sum over arbitrary large powers of the canonical one, because the quadratic differential is a section of the second square of the canonical one. And so you're sort of allowing all powers of the canonical one on the other side, where 8 is. That sort of, it seemed like there was a y squared in this case here, so you just saw two things.
Maybe yes, maybe. I don't know, frankly. In fact, I heard about quadratic differentials as sections of the second tensor power quite recently. I'm not an expert in geometry, but I would be delighted to learn about that. So, let me review briefly a part of what we've seen in the first talk about equational resurgence. So equational resurgence is the first kind of perturbation theory. Not the one that you do in WKB. WKB is concerned with expansions in negative powers of x, but in the previous talk we had powers of, so x is fixed, x is a parameter, and we have negative powers of z. So let me write this. There is a unique, it's a statement, there is a unique formal solution to that equation of that kind, where the coefficients, of course, depend on x, and in that case, they are entire functions of x. But well, let's keep x fixed. X was 1 in the previous talk, when you think of the saddle node. So this is the saddle node case. So you have a unique formal solution of that equation. So let me rewrite the equation. So putting x on the left-hand side like this. It's that equation that you solve. A of z and f naught. So you solve for f naught. You have a unique formal solution, but you have a one-parameter family of trans-series solution. So let me write it like this. F of z and sigma, same parameter sigma as in the first talk. So you have powers of the free parameter, exponentials, which do not mix with the powers. So now you have an array of formal series in 1 over z, exponentials. So exponentials and negative powers, these are trans series. Sigma is the free parameter. So this is the one parameter trans series solution of that differential equation. Let me call it star. And how do you obtain them? You simply plug this into the equation. So this is when the constant term in sigma, and then you obtain something like this: dz f1 minus dya, this coefficient evaluated on z and f naught, but you are supposed to know f naught from the first step, multiplied by f1, so this is equal to 0. It's a linear homogeneous equation, and then you have a hierarchy of linear equations, but the next ones are not homogeneous anymore. So it's the same linear part, except that you have x and 2x, etc. appearing here. And then you have the right-hand side determined inductively by the previous steps. So you have a hierarchy of equations. You find the first one. This is the only nonlinear equation, so then it's rather easy to obtain the other ones. And we are interested in these formal series whose coefficients, all of them are like this, with coefficients depending on x. It is often convenient to replace this solution, depending on sigma, by the generating series, let me call it phi of z and y. So the generating series, I mean, you take fk, and instead of this exponential monomial, you put yk. And if you remember the first talk, we had the same thing. Well, instead of z, it was 1 over z was called x in the previous talk. This was a formal change of variable normalizing the equation. This equation star is conjugate to formally conjugate to a normal form. And this is the formal conjugacy. I mean, y tilde is the new variable. If you take y tilde as a new unknown, the equation becomes simply dy tilde over dz is equal to xy tilde. So this is the normal form associated with the equation. So it's very natural. So now, what is the theorem? So let me erase the first blackboard. Okay, so in fact we are repeating what was done in the first talk with just this non-zero parameter x, and the theorem is the following. First part, the Borel transform of f0, f naught, so the Borel transform with respect to z. So let me call it f naught hat. So it depends on a new variable zeta, and it is defined as by the usual formula. So if you remember, this is called a minor in resurgence theory. So the minor. The statement is that this guy is endlessly continuable. So it's convergent at the origin. And when you follow the analytic continuation, so there is a disk of convergence. And generically, the disk of convergence has radius modulus of x. And the first singular point is at minus x. So imagine x is positive. So the statement is that this is endlessly continuable, meaning the analytic continuation exists everywhere in the large with isolated singularities, and they are located at integer multiples of minus x. So has analytic continuation with singularities only at minus x, minus 2x, etc. This is the first statement. Why is it so? It's really not so complicated. Look at the equation over there and take the Borel transform. Here you are d over dz becomes minus multiplication by minus zeta in the Borel plane. So you have minus zeta minus x f naught hat equal to, well, what is the Borel transform of this? This was a0 of z plus a1 f0 plus etc. So you have f0 hat plus a1 hat convolution with f0. You remember the image of multiplication by Borel transform plus a2 hat and the Borel transform of the coefficients convolution with the power, the convolution powers of the unknown. What are the Borel transform of the coefficient? They are entire function. The Borel transform of an analytic germ at infinity is an entire function. They have no singularity. Where do the singularity come from in the Borel plane? They come from the division by zeta plus x. So first thing you want, imagine you are to solve this equation. First thing you do, you divide by minus zeta minus x. So you create a pole at minus x. Now, well, the equation is nonlinear. It's a bit tricky. But because of the nonlinearity, these convolution with an entire function, this is innocuous. But convolution with itself, if you have a pole at minus x, you must have a pole at minus 2x. Remember, singularities are added by convolution. So this is why the nonlinearity creates singularities at minus x, minus 2x, etc. Simply that. Okay. Next part of the statement is there exists a number, a complex number, let me call it S, such that the alien derivative of f naught at minus x is S times f1. So f0 is the formal solution. f1 is it's the next term, so you compute it. They are known inductively. S, that is something else. S is a number, it's a transcendental number. It's not easy to compute, but while it exists, it's a number. What we are saying here is that the alien derivative is proportional to f1. So what does it mean? Do you remember the meaning of the alien derivative at minus x? It means you take your germ here, f naught hat. You follow the analytic continuation, and here you see a singularity. So here we are encoding the singularity according to a certain recipe. And the recipe is, if here you see a simple pole, properly normalized, the corresponding alien derivative is the unit 1. If you see a logarithmic singularity, so something regular times logarithm, then the encoding is you take the inverse Borel transform of that regular thing, which is the variation. I mean, you have two branches here for the logarithmic singularity. You have a logarithmic cut. You compute the variation, the monodromy. It's supposed to, if it is regular, then this guy is simply the inverse Borel transform of that regular germ. And there is a systematic rule to handle any kind of singularities you can have in the Borel plane, any kind, provided they are isolated. So this is the meaning. And then what about the other singularities? I mean, here you have two branches here. So each of them may have a singularity at minus 2x. What is the result? What is delta minus 2x of f0? It's 0. What does it mean? It means that they compensate. I mean, the two branches, when you take the average, you have no singularity. It means that each branch may have a singularity, but not the sum. And here you have 4 branches. I mean, things like this, etc. And it's the same. The average that you are supposed to perform to define the alien derivation provides you 0 whenever omega is not minus x. It's part of the theorem. Okay? By the way, in the literature you can hear about large order relations. Large order relations. What does that mean? I mean, the series here is f0 is divergent. So the CPs are growing factorially. But how are they growing? Or analogously, how are growing these Taylor coefficients? Well, clearly their growth is dictated by the first singularity. And the first singularity, we know it. I mean, as soon as we know S, we know the first singularity, so we know precisely how these coefficients grow. And we are saying that the rate of growth of those coefficients for large P is dictated by F1. So the large order of CP is given by the low order of F1. This is a kind of miracle which is explained by this resurgence relation. Next part of the statement. I could prove you this theorem, by the way. It's quite easy. It's 2 lines. Let me show you the proof in 2 minutes. So the proof of this statement, you need a lemma. The lemma is, what is the alien derivative of the ordinary derivative? And they are called alien derivations because usually when you are dealing with formal series in one indeterminate, you have only one derivative, or, I mean, it's a theorem. All the derivations in the space of all formal series are proportional to d over dz. And here, because we have restricted our attention to this subalgebra of resurgent series, we discover a huge family of derivations. All these delta omega happen to be derivations, satisfying Leibniz rule, and satisfying no relation between themselves. They are absolutely independent. It's a free Lie algebra generated by a huge number of derivations. No relation between themselves, but they have one relation with d over dz, and here is the relation. Is it plus or minus? Well, we'll see. We'll see if it's a plus or minus. What does that mean, this thing? You remember delta omega of something means take the minor, the Borel transform, follow its analytic continuation until omega, shift the variable, and extract the singularity. This was the definition. Follow the analytic continuation near omega, extract the singularity. This is the guy. And well, and then you take inverse Borel transform, so to speak. Well, what is delta omega of dz of phi? Well, it's the same thing, Borel inverse, singularity of the same thing, but it's not phi hat, it's the Borel transform of the dz of minus zeta times phi hat. So minus zeta times phi hat, so you have two terms. You have minus zeta minus omega times phi hat of omega plus zeta. So clearly you have two parts. One part is minus zeta times delta omega, and the other part is minus omega times delta omega. This is the proof. Consequence of that lemma, so this is the proof of the lemma. Consequence of that, and consequence of the fact that these guys, these operators are derivations, you can apply delta omega to the equation, the defining equation, which is here for F0. So take delta omega of the left-hand side. So that is take, then you obtain dz minus x. It commutes with x, but it does not quite commute with dz. There is this omega. So if I'm not mistaken, you obtain this as alien derivative of the left-hand side. It must coincide with the alien derivative of the right-hand side. Alien derivative of A0 is 0 because you take the Borel transform, F0 hat is entire, the singularity does not exist. So in fact it's the alien chain rule. You have dy of A hat of A, coming out, but you have it's like any derivation, and you have simply delta omega F0. That's it. So this equation is obtained by alien differentiating the defining equation. You started with nonlinear and you get a linear equation, but this linear equation, we know it. It's on the blackboard. When omega is minus 6, this is the defining equation for F1. So when omega is minus x, delta omega F0 is a solution of the same equation. This is why it has to be proportional. When omega is not minus 6, this guy is non-zero, it's not a big deal to prove that it must be 0. When this guy is non-zero, this linear equation has only 0 as a solution. End of the proof. That's third part of the statement, and then we go to parametric resurgence. Third part of the statement. What about the other alien derivatives, these fk's? So we have explained for F0, we want to know what is delta omega of fk. So let me write it at the level of the generating series. Let me write delta omega of phi, meaning the generating series of the alien derivatives. the statement is that there exists a sequence. So for each, so let me say more precisely, for each n which is -1 or 1, 2, etc., there exists a complex number Sn such that delta omega phi is Sn yn plus 1 dy phi if n omega is nx and 0 else. This is what was called the bridge equation in the previous talk. The proof is exactly the same. So, same proof, same kind of reasoning yields to that conclusion. There must exist a sequence of numbers, so-called Stokes constant, and you may guess that this S is just S minus 1, so that these relations hold. Of course, when you expand this relation, this is for the generating series, you are simply saying that delta nx of fm is something like m minus n Sn. I mean, we saw that relation in the previous talk. So we have the large order relations for all the coefficients fk, and we have access to the whole singular structures of the Borel transforms when you follow the analytic continuation. I mean, the nice thing is that you have a closed system of alien relations. You know what is delta of f, but you can know now what is delta of f, or you can iterate those alien derivatives, which means that you are, for instance, look at this. We said that here delta minus 2x is 0 for f0. But delta minus x of f0 is usually non-zero. You can compute it from this. It's delta minus x of f1 multiplied by s, which is something. And this means that you follow, you have here minus x, and then from here you have minus x. So there is a certain singularity here for a certain branch that you can compute. If you know all these relations in principle, you can access to all the singularities of the analytic continuation for each Borel transform. So this is the end of my review of the equational case. Maybe I should say just one word about resummation, because, well, this bridge equation, we like it very much because we have these derivations, these closed formula, and with these mysterious constants, which are very important. If you remember, in the saddle node case, they define the coordinates on the moduli space of the space of all analytic classes of saddle nodes. So this is really a subtle information. Now, there is an interpretation, a very concrete geometric interpretation of these relations. If you think of Borel's summation, you remember Frédéric's description of the Laplace transforms of the Borel transforms. So how does it work? Here, this picture is in the zeta plane. So we have a singular ray in direction of minus x. So we can perform Laplace transform, and we have also singularities in the other starting from x. If you consider the whole family plus x. So this means that for Laplace transform, you can pick any direction up or down, but you won't get the same result. So let me call theta and theta prime these directions, and I could define f theta as the one parameter trans series after resummation. So after resummation, it happens that this happens to be convergent for small sigma and for z belonging to a certain sectorial domain at infinity. So this means Borel Laplace summation in this direction for the trans series, which is here. And similarly, you have another family of solutions. So these are now two families of solutions, two one-parameter families of solutions of the same equation. There must be a relation between them. They are solving the same equation, and the domain of definition are sectors which overlap in the z-plane. So there must be a relation. What is the relation? Here it is. You translate this equation for the one-parameter family Trans series. So this was for the generating series with the y's. If you go to the sigma, to the Trans series, then you have the exponentials. But maybe you remember there was a dotted alien derivation incorporating it. So now it's nice because now you have this simply. So, and in this case, it's just d sigma of f. So this is the bridge equation in that direction for the one-parameter Trans series. Well, it's a fact that these alien derivations were not defined randomly by Ekal. They are defined as the logarithm of the Stokes automorphism. So, I mean, you go from here to here by exponentiating this alien derivation, dotted, applied to f. And you must perform Laplace transform in direction theta. So you do exponential of the dotted thing. It makes sense in a certain graded algebra. You take the Borel transform and you take Laplace in direction theta, which is equivalent, according to the bridge equation, to taking the exponential of s d over d sigma applied to f. Well, this is a vector field we know how to integrate. We get f of z sigma plus s summation in direction theta. So this is the connection formula. So the bridge equation, after exponentiation and Laplace summation, encodes a connection formula between two families of solution. This is a very important message. So, okay, now I can go to the parametric case.
This is kind of the proof of this simple transformation we heard about previously.
Yes. Exactly. This is a detailed explanation for that part of the talk. And I'm doing here only the left side. The left side is easier because there is only one acting derivation. So it's like that. In the other side, you can do the same, but you have many acting alien derivations. So here you have, instead of constant time d over d sigma, you have a nonlinear vector field in the sigma variable. And you must exponentiate it. That means you must compute the flow of a nonlinear vector field in the sigma variable. This is why Frédéric was writing h of sigma. You remember this h? This was the flow of the vector field which appears in the bridge equation when you take the sum of the components. Well, I mean, all this is explained in details in my textbook, for instance. Advertisement. Lecture note in mathematics 2183, something like that. Now let me do the perturbative theory in 1 over x, because this was our starting point. So let's do the second perturbation theory, the one which is relevant for WKB analysis, for instance. So x is no longer fixed. On the contrary, we expand everything in negative powers of x. Z is certainly not fixed either because we are dealing with a differential equation in Z. So we have a statement. There exists a unique formal solution for the same equation, the equation star, which I have erased, of the kind, of the following kind. So it's a sum of negative powers of x with coefficients analytic in Z. So it depends on x and z. So let me call it f naught, but f naught par. It's not the same as before. Before we had coefficients which were entire function of x. Now we have an expansion in x which is generically divergent, nothing to do with the previous one. But as a matter of fact, you can compute inductively these coefficients dp of z. These are analytic functions of z. And we would like to understand something about the Borel transform with respect to x. So let me call xi the Borel variable associated with x. So I mean defined like this. The minor, if you want to do resurgence, in defined like this. Can we guess where will be the singularities in the xi plane? It's really different because look, the equation was something like dz minus x, f0 is a0 plus a1, f0 plus a2, f0 square, etc. When you go to Borel plane in xi, so dz is dz, but minus x becomes minus d xi, d over d xi, f0 hat of xi and z. And here, well, in fact, I'm leaving out something here. I'm missing the constant term. You know the constant term in f0, not the constant term, the p equal to 0 gives you d0 of z times 1 over x multiplied by x, the unit. I have never defined the Borel transform of the unit. But remember, it was something like a pole as a singularity. Well, let me put Dirac. In fact, you can identify the Borel transform of the unit with a Dirac mass at the origin in the xi variable. And so this is just d0 of z. And this should be equal to Borel transform. I mean, these guys depend on z. So it's a0 of z times the unit. So here again, you get delta plus a1 hat, no, a1 of z multiplied by f0 hat plus a2 multiplied by f0 hat, convolution with itself with respect to the xi variable now. So it's still nonlinear with convolution products. And now, well, look at this part of the equation. Imagine for a moment that these coefficients are not here. The solution is explicit. It's simply minus a0 of z plus xi. So where are the singularities in the xi plane? It depends on z. This is parametric resurgence. I mean, so you have the variable of the equation z together with the Borel variable associated with the parameter. So the location of the singularities in the xi plane will move when the variable z moves. So here we need an assumption which is satisfied in the W case and in other cases, and we hope to use that for the holomorphic anomaly equation, for instance. We hope we will do something of that kind. So the assumption is that these coefficients A1, A0, A1, A2, etc., which are holomorphic at infinity, when you follow their analytic continuation, they should have only isolated singularities. The ends have only isolated singularities. So let me call alpha the generic singular point. So we have a set of singularity. I mean the set of singular points alpha somewhere in the complex plane. And so if alpha is one of these singular points, then you see that this guy is singular at xi equal minus z plus alpha. So now we have a huge family of singular points just for that part. But in fact, we should add the correction, the nonlinear correction. So, and you remember, convolution creates addition of singularities. So we should add together these guys. Let me call that guy, for some reason, minus A alpha of z. So A alpha of z is z minus alpha. So I claim that when you solve the nonlinear equation, you see nothing more except the addition of these singular points. So we expect f0 hat parametric to be singular at not only minus A alpha, but also minus A alpha 1 minus A alpha 2. And maybe you can add several of them together. But of course, this will be multiple valued. So when you follow the analytic continuation in the Borel plane in the psi variable, you will see these singular points somewhere. I mean, you are in the psi plane, starting from the origin. And you will see minus alpha plus z, minus beta plus z. Typically, their sum will be somewhere here. So it's minus z plus alpha, minus z plus beta. And typically, you will see the other singularities in the other sheets of the Riemann surface, not for the principal sheet, but well, they exist somewhere. So this is what we expect because of the nonlinearity. So I have no time for the details. Now let me go to the theorem. So similarly to what happened previously, we have a one-parameter family of trans-series solution. So we have x, z, and sigma as previously. Defined like that. It's a sum over n, and you have fn parametric depending on x and z. And you have the same monomial as before because it's the same kind of differential equation. You still have a one-parameter family with defining equations, a hierarchy of differential equations. It's the same as before. And now, theorem. Theorem. So I spent a bit of time in this because with Ricardo, Ines, and Frédéric, we feel that the resurgent community, the modern resurgent community, maybe has not yet seen the interest of parametric resurgence. So, what is the theorem? So, this is the picture. Theorem. Each fn hat parametric is endlessly continuable in psi, so has isolated singularities. So, well, let me rewrite it. Is endlessly continuable in psi with analytic dependence on z with singularities at psi. So now we are dealing with the whole family. So it will be like that, n1a alpha 1 of z plus etc. So it's a huge family of singular points, but not all of them on the same sheet of the Riemann surface. So and these guys, so they can be -1. I mean, they must be integers, at least -1, and the alpha must be elements of this reservoir of singular points. So next question, I remember A alpha is a notation for minus alpha plus z. Next question, what are the alien derivative of the Fn? I mean the alien derivative with respect to x. And now you see that the singular points are moving with z. So we should accept that the index here, eta, depends on z. So what is this? We need a lemma analogous to what we had before for the commutation between delta and d over dz. Well, I skipped the proof, but it's very easy. I mean, it's two lines like before, but it's slightly different. Now, since we are differentiating with respect to z, which is like a parameter if you view psi as a variable, the remainder here, the commutator, is x eta prime of z delta eta of z. Well, I skipped the proof, but there is a commutator, and this is because we are dealing with parametric resurgence, so the index depends on z, moving singularities. Okay, what will you do next to derive the bridge equation? You remember the philosophy? I have a nonlinear equation which defines uniquely this family of resurgent series. I will apply delta eta to both sides of the equation. And delta eta of the left-hand side, I will use this formula. Delta eta of the right-hand side, nonlinear, but delta is a derivation. Alien chain rule. I know how to handle it. I will get a linear equation once more. Let me skip the details and state the theorem. You get this theorem. You can check that. Well, I cannot resist to tell you that when you do this job, at some point you have this eta prime here. You get something like d over dz plus x dy d over dy minus x eta prime plus 1 times delta phi. So I do it for the generating series phi associated with the parametric case. I mean, this is the equation you get when you do what I've said. Phi, and be careful, this is phi parametric now. Phi parametric, delta eta phi. So we get a linear equation, but you see, whether or not the solution will be non-trivial depends very much on eta prime of z plus 1. And it's the same as before. So there is the y d over dy, which produces integers. So eta prime plus 1 minus an integer should or should not be integer. So the consequence is that if eta prime of z plus 1 is not an integer, then you cannot have any compensation and you get an equation which produces 0 because it's a linear homogeneous equation. You prove that this implies delta eta of phi is 0. It's only when eta prime of z is equal to n, an integer at least minus 1, that you may get something. So this is why in the parametric bridge equation you have only n times z minus alpha, n times a alpha, and you get this a coefficient here times yn plus 1 du. Okay, you can prove this. Same kind of reasoning as before, but a very different kind of result. Why is it different? So I'm saying that the only acting alien derivatives, because of that kind of argument, must have this dependence on z. N times z, the eta prime must be integer, and well, the constant term, I call it alpha or minus alpha, and you have, it must be proportional. But be careful, it's a linear equation in z. Everything is authorized to depend on x. So this coefficient, previously we had everything entire function in x, but now everything is resurgent in x. So this guy is probably divergent too, by the way. So this is what we call what Ekal calls the second bridge equation, which is relevant for parametric resurgence. But you see that it's not the end of the story. So you can prove that these coefficients are independent of z locally. Here I'm cheating a little bit. I erased the picture with the foliation associated with the quadratic differential. You know, we had singular leaves in the Q variable. Sometimes they are called Stokes curves. And especially when the curves emanating from the singular points. Which means that in the z plane, there are special rays which should be avoided. So when you are not sitting on a ray, this thing is constant. But there are phenomena which are happening when Z crosses these Stokes lines. This is, in fact, this is wall crossing. So outside of the wall crossing locus, outside of the walls, these guys are constant. Now, it's as before. We have a family of resurgence relations involving coefficients, transcendental coefficients. But now we should wonder, what are the alien derivatives of these coefficients? So we need a third bridge equation. But here you see that now these coefficients do not depend on Z locally, so these omega should be constants. So you can apply the same kind of reasoning, and I have no time now, I suppose. So the idea, the claim by Ekal is that it's not difficult to convince oneself that the indices here, omega, which do not depend on Z, should be of the form multiple of A of alpha minus beta. I mean, multiples of the differences of singular points. And alpha minus beta, if you think a bit, this is a period of our hyperelliptic thing in the WKB case. It's the difference between, well, I mean, you have to figure out. So the claim is that we should expect something like that. In fact, we don't know exactly, we don't understand yet how Ekal produces that kind of equation. So here there is work to be done to understand this third bridge equation. But there is, maybe this will be my concluding remark, there is a conjecture that we have about this. We suspect that this third bridge equation, that we don't understand fully, when you interpret it geometrically like this, should be something like the wall crossing formula that you see, for instance, in Kontsevich-Zobelman work in a different context, or should be the DDP formula, the Delabarre-Dillinger formula in the WKB context. So what is it about? Let me show you one picture. We try to do the same as here. That is, we want to compare the Borel-Laplace summation of the trans-series solution along one direction theta or another direction. So let me say, but something will happen when, so this is the Stokes line. Imagine you have alpha here, beta there, and very far, near infinity, we have Z, but Z is aligned with those guys. And the wall crossing will be something like going from Z1 to Z2, crossing this line. What will it mean for the picture here? It means that when you are at Z1, so you have to think about think about n equal to -1. So we are dealing with minus Z plus alpha. And we are dealing with the one parameter trans-series solution, so we take the dotted alien derivation incorporating the exponential and blah blah blah. We have minus Z plus alpha, minus Z plus beta. So it's the same picture, but at Z1 it's like this. So we have 0 here, and we have minus Z plus alpha, minus Z1 plus alpha, minus Z1 plus beta. And 0 is like this. I'm just relabeling the points of the same picture. So it's like this. And I have one direction here and one direction there. Let me call it theta sup and theta inf. And I want to compare the f theta sup with f theta inf. So it depends on x, z, sigma, and it should be connected somehow with the other family. When I do this computation, you see I have to cross two lines. I must cross this, so I have to compose two Stokes phenomena. So let me use an intermediary direction theta, or let me call it, well, theta will be the direction of alpha minus beta. So let me call theta this direction, so this will be theta prime. And this way I can write the formula like this. F theta sup is exponential of the dotted alien derivative. I integrate the vector field and I get f theta prime composed with respect to sigma with some h associated with beta, because I cross first the beta singular ray. But here, well, when I exponentiate and I take the Borel-Laplace sum, I must take the Borel-Laplace sum of p beta. So let me say it's p beta, but it's p beta inf, because it's a Laplace summation below theta. And similarly, f theta prime is the same as f theta inf, composed with h alpha still below. So this is the result. You are composing two Stokes automorphisms obtained from the second bridge equation, but each of them requires its Borel-Laplace summation, because each of them involves divergent series. But the thing is that when you do the same thing at Z2, so this was at Z1, but at Z2, the picture is reversed, because now we have alpha minus Z2 plus alpha minus Z2 plus beta, and now 0 is below. So this is theta. This is the picture at Z2. So now there is a difference of order. When you go from above to below, you cross first the alpha ray and then the beta ray, and there is a second difference. The second difference is that when you do the computation, you find so alpha first and beta second, and you observe that for beta it is still the below summation, but for alpha it's the above summation. It's a different Laplace, it's a different summation of the same Stokes coefficient. So this, and in fact, this relation should be the same. So we expect this relation that h beta summation inf h alpha summation inf should coincide with h alpha summation sup h beta summation inf. And so we suppose, to be consistent with wall-crossing formula in Kontsevich-Zeubelman or with DDP formula, we suppose that this guy has to be h alpha inf composed with something. Let me call it G. So this is very conjectural, but this is to try to make a relationship with different kinds of works, and this is what we are exactly trying to extract from Eckhart's work of 25 years ago or 30 years ago. Well, thank you for your attention.
So maybe I can try to elaborate on what I was trying to do in the beginning, and actually I wish I could rerun your lecture once again, sort of thinking about it in terms of Higgs bundles. Because I think that the parameter that you have y should be thought of as a parameter on the cotangent bundle of whatever plane you're looking at or Riemann surface. Mm-hmm. And then the decomposition in powers of y exactly corresponds to looking at various powers of the canonical bundle. And now I think it looks like much like what we're doing with Sergei when we're trying to quantize the Higgs bundle moduli space, where it becomes very significant that there is this sort of splitting of things in homogeneous degrees along the cotangent fibers. And I'm wondering whether your parameters are somehow parameters that parameterize this Higgs bundle moduli space. And do you know, so therefore, do you know what topology these parameters are? I mean, what do the total space of them form, or is it just simple, any parameters goes, or is there some topology to the space? And in particular, does it have an integrable system?
In fact, I would love to understand the connection with what you are saying, because here I was very analytic. I mean, I was very much with... So formal series and resummation. It's true that after resummation, there is something convergent, something analytic. So we expect in the variable y to have some kind of local convergence, but maybe if the equation comes from a global problem, this should be explored better. So I mean, at our level, we managed to give a meaning to these formal objects when x is in a certain sectorial neighborhood of infinity. Maybe x is positive and large, for instance, and y is small. Y, the cotangent bundle variable, should be not so locally. We have something. We have so we maybe have a disk in the fiber, at least in which things make sense analytically. I don't know if that answers your question about topology.
I'm also somehow not particularly precise, just seeing very strong similarities. I also think there are strong similarities to, if you look at Naitzky's work on spectral networks, and of course the corresponding Stokes phenomenon and so on. It seems to be sort of maybe dual languages on the same thing. And their Higgs bundles play a significant role somehow in understanding the whole formalism, and give specific coordinates on the parameter space in which it's particularly simple to understand the phenomenon, for example, of wall crossing.
I would love to hear more about that. So we have, in principle, a bit of time during these 2 days, this afternoon, tomorrow. So we should try and find a moment to have a more detailed discussion, maybe either in this room or in another room, because in fact I'm very ignorant about Higgs bundle and Naitzky's work, but I would love to understand it better. Yeah.
You should have been here.
Yeah, but we invited many people, not everybody could make it, and it's true that we didn't, initially we were thinking of a more European-centered meeting.
No, sure, I'm not sure I can faithfully reproduce all his things, but it certainly reminds me a lot about it.
But we are trying to read Naitzky's. I mean, there is the famous Gayotto-Moore-Naitzky's paper, for instance, and this is definitely in the landscape we want to understand. So that's absolutely relevant, for sure.
More questions? Oh, okay. If not, let's thank David again. And so, for lunch, just follow each other who doesn't know to go to Scuola Normale canteen. The afternoon there was a slight change because Sergei had a last-minute problem, so he can't come. So just look at the schedule. And as David just said, there's lots of rooms for discussion. So let's make the best of the free time we have.
Of the first day, and we'll have Ricardo speaking about coequational parametric resurgence in topological strings.
Okay, thank you. Thank you very much for the invitation. Back to Pisa after 2 weeks, I think. And so I want to do a little bit of a follow-up on what David was telling us this morning concerning this story of coequational and parametric resurgence, because that likely, in spite of the fact that, as David motivated, it has its origin within WKB. Sorry, what's going on here? Although it has its origins in these things of WKB, very likely probably the best setting for using parametric resurgence will be within topological strings. So this is sort of work that's been going on with our group, and I'm sort of doing a detour over these papers which are highlighted and upcoming work. All right, so string theory generically is defined perturbatively, so in powers of the string coupling, 2g minus 2, and this expansion is asymptotic, which means that these guys, this fg, they grow factorially fast, and this series has a zero radius of convergence. And so in that in itself, it's a whole problem that should be addressed and will be addressed partially. But the question that I want to sort of motivate here is what happens when the string theory, this is the free energy of the string theory, when the string theory that I'm thinking of is A-model topological strings on some Calabi-Yau threefold. In that case, at least in the large radius phases, the genus G free energies themselves have well-behaved definitions. This is convergent. You can compute functions out of this. And when you do the expansion in terms of exponential of minus t, t here is the Kähler parameter, the guys that you find in front are rational numbers, which are...
It's exponential minus t.
Yes. Oh, no, yes, you're right. There's a d missing here. Yeah, sorry. Yes, it's of course in powers of exponential of minus t. And these numbers in front, they're rational numbers. They're known as the Gromov-Witten invariants. They're enumerative invariants because they're counting, well, they're rational, so it's sort of a virtual counting, the number of Riemann surfaces of degree d and genus G which you may embed into the Calabi-Yau threefold. So the question that I want to start off with, if these guys grow factorially fast, what does that imply to the growth of these invariants, either in genus or in degree? So that's the question I just made. And here's a table. The table is for the example of local P2. We'll be back to this later in the talk. And this is a bunch of Gromov-Witten invariants. They're all rational. I'm just putting decimal points here just to make it easier so that you can see. So what's going on? And what I'm having here is genus and degree. So here's an analysis of the growth of these numbers, just numerical. So if you have fixed genus, and you look at the growth in degree, basically you're plotting here the log, so there's basically exponential growth. It's not factorial. The same thing happens with this red part here. So I basically fix degree, look at growth in genus, nothing specially happens. So for fixed either genus or degree, there's no factorial growth. The factorial growth, this factorial growth, is hidden in the diagonals of this table. If you pick any diagonal, this is the green line here, the resolution's not great, but if you pick any diagonal, here we're plotting DD, the main diagonal, then you find factorial growth. Okay? Can we make this more precise or not? So let's try to see how to do that. So in order to try to make these things more precise, let's go back to the talks of this morning, and let's address this in the context of resurgence. So just a quick overview or review of what was spoken about this morning. So I'm dealing with some object which is asymptotic. The coefficients grow factorially fast. I don't care if it's 2g factorial, g factorial is all the same. And I'm doing an expansion in a coupling z, which is taken near infinity for, as you've seen in this morning's talks of Frédéric, for some formulae look slightly nicer. So the Borel transform removes the factorial growth. So all I'm left is with subleading exponential growth, which leads to a non-zero radius of convergence. And ideally, I would want to do a Borel resummation to get back my answer. And this is done by Laplace type integral, which everything is fine as long as this ray does not hit a singularity. The singularities, this was also discussed this morning, that you may find on the Borel plane, so where you would have to avoid the contour of integration either one side or to the other, can be very general. Frédéric mentioned a little bit, also David, this business of endless analytic continuation. We're not going to be worried about that. We're going to be just focused on a specific class of singularities, which is all the ones that matter for the things that we need to do, which are so-called simple resurgent functions, which are associated to, if you want, simple singularities. This means that each Borel singularity is a simple pole and a logarithmic branch point. Looks like this. I'm not putting the simple pole because it's trivial, just want to focus on the logarithmic branch point. So here's the log branch point. Whatever, this is near some singularity, so there's some extra holomorphic content, there maybe there or not. And in front of the log, there's also going to be some holomorphic content. And the art of this business is to write the holomorphic content as the Borel of something else. This is locally well defined next to that point, up to some number that may appear here. And now I can be completely precise as what happens when I cross a Stokes line. So if this is my Stokes line where singularities are located, and I need to avoid the contour either on the left or on the right, there's a difference between the integration here on theta plus and the integration on theta minus, which is associated to this sum over all these Hankel contours. And because I know what's going on each Hankel contour, there's just a log, it's triviality to the integration. So the difference between the resummations, the inverse Borel transforms, is just a sum of these numbers times exponentially suppressed stuff, z is very large, times the resummation of, of the art of the business, which was to write this here in front as the Borel of something else. And so I can write a discontinuity like that. And what this essentially is telling us is that the perturbative series is not enough. Every time I start going around on the Borel plane, I cross discontinuities, and everybody else must come along for the ride. All right, so we want to apply this in string theory, and for most of the talk, I know I started with the A model and this discussion of Gromov-Witten invariance. For most of the talk, I'm going to be focusing on the B model because that's where it's really easy to, well, not really easy, but simpler, to generate large order data, and so to put the machinery of resurgence at work. There's many advantages of using B model because in some specific classes of geometries, they're dual to matrix models where things are easy to work out. But I'm not going to be focusing too much on matrix models, so let's not worry about this. All right, so I'll give you a quick overview of resurgence, string series, and asymptotics. This was not covered in the morning because the asymptotic part is what I want to make focus on. Then I'll tell you a little bit on how to use this machinery in the B model topological string and how to compute large order data, look at the asymptotics. We will see that when we look at the asymptotics, we'll learn that coequational or parametric resurgence is really important. And then at the end, we'll come back to the asymptotics of enumerative invariance. All right, so we already saw this a little bit this morning. So analytic functions are described by power series, and so if I want to go and describe non-analytic functions, I need sort of augment monomials with transmonomials. And here are some examples of transmonomials I can use. So I'm always doing perturbation theory about z equals infinity, remember? So there's the usual exponential, there's a log, and then I can start iterating all these people, and I can produce arbitrarily complicated transmonomials, and then by considering all the powers of these guys, I construct trans series. That looks a bit nasty. Happily, for what I have to say today, we only care about the exponential and the log. We don't need to iterate anyone, although in harder problems that might be required. And so we can build up the trans series. Here's a trans series. We already saw it with a different notation in both the talks of this morning of Frédéric and David. The Fn's, of course, the F0 is just a perturbative power series that I started off with. And the Fn's will be the instantons. So there's the nth instanton with instanton action A has the familiar non-analytic term. Remember, z is near infinity. And then next to each, to the n instanton sector, I can still do a loop expansion, powers of g, one loop, two loops, so on, and construct, there will be yet another asymptotic series attached to each instanton guy. With a, and not necessarily all the series start at 1, so maybe some start at some different number. So this is in some sense going non-perturbative while staying perturbative, because this has a non-perturbative term, but it's constructing all of these as a double perturbative expansion in powers of 1 over z and perturbative in powers of the transmonomial. Sigma here is a trans series parameter, which from the point of view of just setting up this one parameter trans series is sort of an instanton counting parameter. But if you think of this as a solution to a differential equation, this is parameter one first order differential equation. You can think of this sigma as the degree of freedom associated to the choice of boundary condition, or if this was an integral, a choice of integration contour, and so on. Anyways, this was a little bit discussed this morning. And the trans series then is a very general solution to a nonlinear system, because I can just grab these ansatz, plug it into my equation, whatever I want to solve, and crank the wheel, and the computer will be generating all these coefficients for you. The statement of resurgence is that all these coefficients that you can generate are not independent of each other. They relate to each other at different instanton number, at different loop order. And so the slogan usually is that you can obtain non-perturbative data out of perturbative data.
So question, is the n here anything to do with the g and n? Is that anything to do with the topological recursion g and n?
No. So the topological recursion, basically what it's doing, it's generating for you just the perturbative part.
Right.
So, and that recursion in itself will be very similar to, the result of that recursion in itself will be very similar to what you get here, because you're going to get the perturbative series, which is asymptotic. And at least in the case associated to matrix models, it grows as 2g factorial. I don't know. I think you have a generalization. I don't know if also, I imagine it also grows factorially. I just don't know how fast factorially. And that will imply that the recursion itself should be augmented by these guys.
Yes, so
but this is extra to the recursion.
And so here in the previous slides, we don't see n at all, we just see g, because we saw the FGs.
Okay, let me just...
Right. From the beginning, we just saw FGs. And
so for instance, here, this would be F0.
Yes.
It's just a perturbative.
Right, and also that FT could probably be fitted into topological recursion, right?
Oh, definitely. The topological recursion would tell you what these guys are.
Exactly.
And out of the asymptotics of the topological recursion, you'd get the other guys out. All right. So now a technicality, because this, you know, if I was to give a standard talk on this business, I'll never go into this slide, but this is going to be important to make a connection to what David was talking this morning on coequational resurgence. So let me just make this detour. So we had a discontinuity. That was this plot when I cross. And the discontinuity operator is a nice operator, but it can be improved. You can think of the discontinuity as the first approximation to a better operator, which is the pointed alien derivative that was already discussed earlier today. So what's the idea? The idea at this level is just that let's rewrite. The discontinuity tells me the difference between the left and the right, like that. But I can just say that the left is equal to the right after composed with some operator, which will be an automorphism, because it's the one that allows me to pass from one side to the other. And if it's an automorphism, which is usually denoted by this funny letter, then it's the exponential of a derivation. That's how we'll define it. And the derivation, it's the log of 1 minus this. So it's basically the discontinuity, and then iterate the discontinuity, and iterate the discontinuity, and so on. So let's imagine that we improve the discontinuity and make a derivation. This derivation satisfies Leibniz rule, either for the standard product when you apply it to the business we're doing here, or to the convolution when we apply it to the Borel transforms. And there's a direct definition that I think Frédéric and David vaguely mentioned. We'll further decompose. So this holds along an angle theta. There's a theta here, but there's different singularities along theta. So we'll decompose the alien derivative with derivations associated to each location. And then it's a long story that I'll try to make short, that you can compute this alien derivative easily, because of the Curie property that actually David proved for us this morning. It commutes with ordinary derivative. In fact, instead of that z, I should have written that derivation in sigma. And so if f is a trans series for solution for some first order ODE, both the derivation with respect to alien omega and derivation with respect to the parameter, not with z, that's a typo, they must satisfy the same linear ODE, which means that they're proportional. And the constant of proportional, or the function of proportionality, may still depend on sigma. The ODE is in z. And this is basically the gathering of all Stokes coefficients, or the bridge equation. And we can decompose this as it acts on each element of the trans series. And it looks like that. So basically what we see here is that we have a relation between the nth sector and the nth plus k sector up to so-called Stokes coefficients. From the point of view of the Borel transform, the Borel of the phi nth sector near the kth singularity, let me read it here, at the kth singularity of the Borel n instanton sector, the k singularity of the n, one finds the resurgence, thus the name, of the Borel of the n plus k, next to the log branch cut. That's how you see all these people coming and going. Of course, we still need to know what these numbers are. They're usually hard transcendental numbers, but let's leave it under the rug for the moment. And so this derivation that you have up here is basically inducing motions along the trans series. There's only one way to go forward. There's many ways to go backwards. Just a picture to have in mind. As a bonus, this also describes for us Stokes phenomenon. So basically, when I act along the zeroth direction, the forward direction, I only have one motion forward. And the reason that, and that is the reason why I basically only have to exponentiate this derivative, which becomes the standard dd sigma derivative, which creates the standard automorphism, which is just a shift. This is the Stokes phenomenon, right? If I had sigma equals 0, I only have the perturbative series. If it turns on, the exponentially suppressed guy come along. Along pi is harder, and let me not talk about it. Resummation, just one word on resummation. So now we go back to the genus expansion in string theory. They grow to G factorially fast. How can I resum it? Now this is done basically in 2 steps, or 3 steps. We build the trans series, so we need to include all these n guys. This is still to be computed. And we'll see how to compute it. It needs to be slightly more than what we use for the perturbative calculations. Then we have to Borel resum it. In practice, we do Borel pave. We don't know all these guys, so we don't actually can compute analytic expressions for these guys. So we have to do an approximation. Pave approximate is the best. In fact, after that, we also do a numerical integration. So there are sort of 2 numerical procedures here. And then we put everybody back into the trans series. Hopefully, this will work. In fact, it does. I will tell you a little bit more closer to the end that we can reach arbitrary coupling. In fact, arbitrarily strong coupling, and go into complex plane of all the parameters if we properly incorporate Stokes phenomena. All right. Now, the link to asymptotics, because somehow what we're going to be, I mean, we don't have theorems when we're doing topological strings, so we cannot just prove that the function is resurgent. So we basically test it when using analysis of the asymptotics of the different growths of the perturbative series, the non-perturbative series, and so on. So let me give you a couple of words on asymptotics. The perturbative sector. If I just use the alien derivatives I've just computed, which is the same as computing these discontinuities, I can evaluate it exactly. And then I can just write down some Cauchy dispersion relation for f0 of z, such as to extract the gth component in the trans series. And I can find something like that when I plug in here for the phi l's, their L instanton series. This is a relation that I find here. I'm not writing it all completely right. And what we see is that there's some proportionality factor, that's just the Stokes coefficient, but then at leading order the growth is factorially fast. Next to leading order it's exponential. And then I start having the 1 loop around the 1 instanton, 2 loop around the 1 instanton is suppressed in 1 over g, and so on. And then I can go to the 2 instanton is now suppressed in 2 to the minus g. There's still a factorial growth there. Then the 1 loop around the 2 instantons, 2 loop around the 2 instantons, and on and on and on. So basically I have a picture that tells me that if I know all these instanton contributions, I can predict the larger the behavior, the larger the growth of the perturbative sector. But the idea of resurgence is that these green arrows should not only go in one direction, meaning that I'm not only predicting the larger the behavior, but I should also be able, if I know this sequence well enough, I should be able to decode the non-perturbative content, which is hidden in that sequence. And that is, in some sense, the philosophy behind constructing the trans series we'll be constructing for topological strings. Of course, these relations are true up to the need to include the Stokes coefficients. And these sometimes are hard, and sometimes are not. In our cases, they're always hard. The advantages of of this business is that I can do this for any sector I so choose. So here I'm looking at the 3 instanton sector, and if I want to learn what it's going to be its asymptotics, it's going to have contributions from everybody forward. And remember, when I'm moving around this alien chain, I only have one motion forward, so this is sort of easy to include. It's almost like the perturbative. But I also have contributions from the guys that were there before. And if you remember the drawings I did on this alien chain, there's many paths going backwards, and this is usually a mess. So let me just look at the leading terms. So again, forward, it's just like before. Backwards is a little bit hard. And you see that here for the n instanton guy, I have something which looks at the leading order. It's controlled by the nth plus 1, the next one. And also I have contributions coming from the one which is previous. And this is up to a sign of minus 1 over minus 1 up to the power g. It's also the same instanton action that's here. So this is almost the same order. And this is controlled by the guy that was before. In string theory, in string theory, there's always more than one instanton action to consider. So if there's more than one instanton action, I need, instead of having motions, instead of these alien derivatives giving me motions in a chain, they give me motions in higher dimensional lattices. There's basically one motion forward. Here I'm depicting elementary motions on a 2-dimensional lattice. There's many backwards. And the reason why string theory is always has at least 2 instanton actions is because it's resonant. This means that this is what the perturbative will always look like, even in the simplest possible case. The perturbative guys, they grow as string coupling squared. So there's a phenomenon which is known as resonance, where both instanton action A and instanton action minus A must always come into the game. And here's basically the reason in looking again just at the leading growth of such an asymptotic series. So let me tell you that this would be the case if I only had instanton action A. So the Stokes coefficient, the factorial growth, the instanton action, the one loop, the one instanton. But if I also have a minus A here, then I have this contribution with a minus A. And basically there's a relation between these guys in string theory that tells me basically that all the odd guys are 0 and the even guys are not, and that's how the GS squared expansion comes about. And there's formulae for these, and there's formulae for all these that I'm just showing you pictures instead of formulae. So basically, this type of asymptotics, resonant asymptotics, resurgent asymptotics, have been found in many examples, a bunch of them, and basically we're going to be converging towards the examples of topological strings and see how these things go on. Of course, the general picture might be really hard. I have no idea how to describe asymptotics of this picture, but that conveys the idea. All right, so now we want to apply all this business to topological string theory. And the reason, the motivation I had at the beginning was to look at the growth of Gromov-Witten invariance in the A model. But sort of the easier, again, it's not necessarily easy, but well, path towards generating large order data is within the B model, where I will be exploiting the holomorphic anomaly and the holomorphic anomaly equations to generate data. So let me talk a little bit about that. So just a word on what is equation. I'm not going to go into any detail, so let me just give you a word of why these things are useful or needed. So we're going to be looking at the B model on some local Calabi-Yau, mirrored to some toric, and this is just a technicality such that all the non-trivial information is encoded in a Riemann surface. Well, it's a technicality that makes things life much easier. And the string free energy is what the string free energy looks like once again. Z now is the complex structure modulus or moduli, depending on which case I am. And here's G string. And the story of the, in two slides, the story of the holomorphic anomaly is that these guys do not have just a dependence on holomorphic coordinates Z of moduli space, but also on holomorphic coordinates Z bar. This goes back to 1992. And the reason for this is basically that moduli space of genus G surfaces has a boundary. So if I compute the anti-holomorphic derivative of any of these FGs, it's given by integration over moduli space of a total derivative. And this total derivative is not 0 because of the boundary. Here's a picture of the boundary, which leads to the holomorphic anomaly equation. So if I have some genus 2 surface, here's two ways to pinch it and to reach this boundary. One is just to collapse here in a cycle. I get a surface which is still connected but has one less genera. So this is sort of this Fg minus 1 that appears here. This is the schematically holomorphic anomaly equations. I'm not telling you a lot about it. Or I could just pinch in between, and I get disconnected surfaces, but where the sum of the genus is still equal to the initial one. G minus H plus H gives G. Okay. This is sort of the structure. This is a covariant derivative, and that's the idea. All right, so this has been solved perturbatively. I mean, Albrecht has extremely nice papers on this story for this example of local P2. And basically, here's the equations now in full form. S is some variable that we call the propagator variable. It includes both holomorphic and anti-holomorphic dependence. So it includes the Z and Z bar. All the Z bar is there. So if you don't want to go into technicalities, just think of it as the Z bar. And these are some covariant derivatives in complex structure moduli space. Let's not worry too much about it. And so Albrecht and his students just computed a lot of these FGs. What would like these you can check. We'll show you soon that they grow factorially fast. There's instanton actions controlling the growth of these guys, and we would like to compute the non-perturbative analogs of these guys as well. So how can we do that? What would the non-perturbative holomorphic anomaly equations look like? Well, again, this was the question I was just saying. So if you have enough perturbative guys, you can ask what the large order behavior is, and immediately you can ask very naive questions. For instance, in the holomorphic limit, do I have some anti-holomorphic instanton action that also, just comes back to my standard holomorphic action? Do I have something that looks like that? Maybe. What can we find? Well, the first thing is that the equations as they're written, they're essentially useless from the point of view of train series, because they're written for each coefficient. And in order to generate a train series, I need an equation which, where I can plug ansatz, where instead I can put the power series, or I can put the train series, or whatever else. So the first thing that should be done would be to rewrite the holomorphic anomaly equations, say for the partition function, because then I could put in some natural train series ansatz and try to play this game. This is possible to be done. So here I'm just doing a complex structure moduli space of dimension 1. So there's a single Z and a single S, or a Z bar, whatever you want to call it. And basically it looks like heat equation. I mean, that it should be of heat equation form has been known for a long time. There's some initial data that needs to be added. That's just to ensure that the limits here are properly taken care of. But that basically comes in at low genus. At higher genus is essentially a heat equation. And if I just plug in for Z, just the exponential of the perturbative, I get back the holomorphic anomaly equations. So what happens if I plug in for Z exponential of some train series?
Just a question, so I guess Witten was the one.
Yeah. This would be Witten.
That's what I was about to
Yes.
remark. And so why are these other extra terms?
Yeah, it's just a technicality. It's just because if you just put the heat equation, nothing else, this sum will start at 0 and will end up G. It's just a detail. It doesn't really matter.
But in fact, Witten writes it 9. His sum starts at 0.
Yeah. But it's just a stupid mistake. I mean, but it's nothing very deep. And as I said, this thing is really only important at low genus. So, I mean, at high genus, the heat equation is the idea. All right. So what happens if we insert the train series ansatz instead? Hopefully, we're going to get a recursion for all these guys. The first thing in the recursion is this equation. Derivative of S of A is 0. So the instanton action is still holomorphic. That's a really nice result, because that means that we can still compute A as an appropriate combination of periods in the geometry. And this was a conjecture that was already in the literature, that the instanton action should be periods. So that's great. What about all the other coefficients? Well, here's the equation. Let's not dwell a lot on it. But you see that the structure is very similar. There's a derivative in the anti-holomorphic, which is sort of quote-unquote covariantized. There's the differential operator. There's actually a bunch of them. I'm not telling you which they are. You can find it in the paper. And then there's sort of a quadratic piece, which is, again, quote-unquote covariantized, with regular derivatives. That's the machine. So I'm not sure I want to do this interlude. Probably not. Let's just jump this. And then I can plug in, just look at the structure of the equations and start solving them. I mean, the equations are not so hard. So for the perturbative topological string, the solution, this is the general solution. It's a polynomial in S of degree 3g minus 3. Of course, the coefficients, holomorphic functions that still need to be defined. So, I mean, I still need some boundary conditions. Boundary conditions are usually associated to comparing to the conifold, as Albrecht taught us a couple of years ago. And for the non-perturbative topological string, this is what things look like. There's exponential terms. These come from the fact that I no longer just have DDS, but I have DDS minus an action. And then there's polynomials in S of specific degrees. Again, there's going to be holomorphic terms that I need to fix, and we do boundary conditions, also comparing against the conifold, because the conifold can be solved exactly non-perturbatively. We can write down a term series to all orders. So these are just the comments of the slides I just jumped off, that same calculation can be done for the Nekrasov-Shatashvili limit. If anybody is curious about it, then we can talk later. It's not really required for the main purpose of this talk. Okay, asymptotics. So here's a test that we did, but could have been done earlier only with the data you had. So what are we doing? The green dots are just basically, I'm looking at, let me go back here. I'm just looking at the growth of the perturbative. And I look at a lot of data, and I extract what A should be. That's each of these green dots at different points in moduli space. Let's go back to that picture. So I'm varying moduli space. This is the variation of the coordinate on moduli space. And I'm telling what the imaginary part of the instant on action should be, just out of large order. And I see all these green dots. And now, the goal would be, or is, can I predict an analytic expression for this growth, for the instant on action? And here's the result. So we go near the conifold point, which in the usual original coordinate is at minus 127. We actually, for all these tests, turns out to be more useful to use this psi coordinate. Basically, I have 3 conifold points at roots of unity. And the instant on actions are going to be just the periods at near this point. So basically, the solution of Picard-Fuchs. And the solution of Picard-Fuchs gives you this flat coordinate TC. Depends here on psi. It's some complicated hypergeometric. It doesn't matter what it is. It's just that plot, the blue line. And the instant on actions are associated to the cubic roots of unity at each, always using this function. And as you can see, the prediction is just spot on. In fact, we have this to extreme numerical precision. At some stage, the large ranges kick in. I'll tell you about that in the next slide. But let me just tell you one more thing about these things, is that this is the plot where they look like. So basically, I see branch points and cuts of the instant on actions in the psi plane. Each wedge here is, of course, one full complex z plane. But here I have for instant on action 1, instant on action 2, and instant on action 3. The fact that at some stage there's a change of dominance, which again, it's clearly seen, no problem, is associated that the conifold is not the only singular point on moduli space. There's also a large radius point, whatever coordinate you prefer to use. This is where the Kähler parameter becomes large. And again, if you solve Picard-Fuchs, write down the mirror map. That's what the flat coordinate would look like, the Kähler parameter. And in the region of moduli space of large radius point, you probably can see it here, I basically have the Kähler instant on action. And it takes dominance. This is, you can do this on the Borel plane, see it a little bit nicer what's going on. So what am I plotting here? These are Borel planes, and I'm varying psi. So I'm varying the coordinate on moduli space. And the dots basically are the would-be Borel branch cuts. Of course, I don't know the exact Borel, so I do a pavé approximant to the Borel, and these cuts are implemented numerically as a bunch of dots. Those are the dots that you see around. And the curves is sort of the trajectory as I vary the coordinate on moduli space of conifold action 1, conifold action 2, and Kähler. And you see that here I have conifold 1, I have conifold 2. Conifold 1 is closer to the origin, so it dominates the large order asymptotics. It keeps going. I can see the scalar there, still there, and then it's gone. So the structure is non-trivial in some sense, and this is probably the first hint that parametric resurgence needs to come into play. Is that some, let's say, Stokes coefficients or Stokes residues associated to each of these branch cuts, at some stage they vanish. So they're sort of varying over moduli space. All right, but somehow, again, this is a test that could have been done with the data that Albrecht generated in 2008. But can we do more tests? Can we look at the rest of the train series? Here's the one instanton sector. Can we check if it's, again, as I said, I don't have a theorem saying that the solution to the holomorphic anomaly equations is a resurgent function. So I'm testing whether it is or not, in which way it is. Even if I had a theorem, I mean, these relations in themselves telling us how to generate non-perturbative data out of perturbative data and vice versa are of course very useful. So that would be the prediction that comes out from the holomorphic, the non-perturbative generalization of holomorphic anomaly equations, where everybody is, all holomorphic ambiguities, let's say, have been fixed. And I can test this at large order using this sequence. So basically, I'm looking at the large order behavior of the perturbative, and I'm extracting the instanton action, I'm extracting the factorial gross, so that I get the one loop around the one instanton. I'm using this notation E1 just to remind you that I'm looking at conifold 1, not, there are 3 conifold singularities. Then I can start, I can test h equals 0. Then I remove h equals 0, I can test h equals 1. I remove it, I can test. So we're going to do the test for the first 3 guys at 3 different points in psi moduli space. Those are 3 different points. Let me show you the tests. Let's go back to see what are we plotting here. So 3 points in moduli space. 3 points in moduli space. Then I'm doing this for h equals 0, 1, 2, and 3. That's 0, 1, 2, and 3. Okay? Now what are each of these plots? X changes the value of the propagator around its holomorphic value. So I'm changing S. Here I'm just changing S and seeing how things go. And then there's 2 plots on all these figures. And basically blue means that I'm looking at the real part, and green means that I'm looking at the imaginary part of these things. They're all complex. The dots is what comes out of numerics. The lines, the dashed lines, is what comes out of our analytic predictions. I think it's convincing. So, great. So the one instanton sector seems to be holding very well. How is the 2 instanton sector holding? So, if it's holding very well, and if we just used standard resurgent, let's say, equational in the parlance of David this morning, or if you want, bridge equation 1, so far you say, there's no parametric resurgence yet. So let's look at the 2 instantons. At the 2 instanton level, here's what the holomorphic anomaly equations have to say. This is what it looks like. And again, let's imagine we computed everything. But that's not all the story, because as I said, string theory is resonant. So there's always A and minus A coming along. So there's also a mixed contribution here. Can I test these things? Here's a sequence that I can use to test. I'm looking at the large order growth of the one instanton. And that leading order, it's controlled by the forward guy and the mixed guy. The only difference between the forward and the mixed is this sign here. Everything else is basically the same weight. All right, let's make these tests. Again, let me show you the figures. Let's discuss what's in these figures. I'm always at the fixed point in moduli space, just to make it simpler. And I'm also varying S. Okay, so this is several tests at the same point, and I'm always varying the holomorphic, the S coordinate around its holomorphic value. And what am I plotting? The top figure, I'm looking at the pure 2 instanton, and in the bottom figure, I'm looking at the mixed one. Okay? There you go. Real and imaginary parts. That's why we have to. I think, again, this is very convincing. So you would say, okay, look, there's no parametric resurgence here. Let's dig deep into the asymptotics, or deeper. Because, in fact, there's no reason to see any hints of co-equational or parametric resurgence yet. So what have we checked? At 2 instanton level, we've checked the validity of both these pure and these mixed contributions, analyzing the large order growth of the 1 instanton. You could have asked already, why did I put hats on these functions? I didn't put any hat yet. What does the hat mean? The hat is associated to the way in which I fix the holomorphic ambiguity. And this is not fixed in the standard way where I compare against the conifold. This is fixed by requiring a vanishing holomorphic limits to all orders. That's what the asymptotics are telling us. The large order relation here, I'm writing it very schematically because I'm just writing it for the, one permitted trans series. But what I want to say is that it involves a single alien derivation. So I'm looking at the large order growth of the 1 instanton, which is dominated by the 2 instanton. It's the hat because I've changed sort of boundary conditions. And this is associated when I go from 1 to 1 plus 1, it's one alien derivation. So I'm moving one step forward. And the one step forward somehow never sees parametric resurgence. The surprise, which is hidden deep into the asymptotics, is that the same 2 instanton sector should control at next to leading order. So upon Borel resumming this guy and removing it out of the perturbative, so it's the subleading, the exponentially subleading growth of the perturbative. And in equational resurgence, this is the same person. This is the same guy. Let me also say that this involves 2 alien derivations. I'm jumping from 0 to 2. The numerics, however, tell us, no, that's not the hatted guy. That's the tilted guy. There's a standard 2 instantons fixed against the conifold, but I also need to have an extra 2 instantons fixed against vanishing holomorphic limit. This is what I've just said. It's written here. So these are not the same. So you could be worried because you say, okay, resurgence doesn't work. But upon second thought, it did not have to work equationally. It had to work co-equationally. So what does that mean? This means that, again, this is a surprise from the viewpoint of equational resurgence, because all I have is a single bridge equation. This is the bridge equation that David called bridge 1 earlier today. When I go to co-equational resurgence, I have an equation that looks just like that. Not exactly the same, but just like that. But I also have what David called bridge equation 3. So the Stokes data also satisfies the bridge equation. So when I take a second alien derivation, and here I'm doing things very schematically, if I just have that, this is what I have. I should have a single contribution here. But if I have co-equational resurgence, this derivation will give me an extra piece. And hopefully, this is work in progress, this will explain this mismatch. So this should be the origin of the need for co-equational resurgence within topological strings, and in principle, because asymptotics is already telling me what are the 2 contributions, it should be already telling me what is bridge 3 in this example. All right. So you could say, fine, needs to be going, need to do the 2 instanton sector, but we already have the 1 instanton sector. That's valid. That works equationally, co-equationally as you want. What can we do with it? So let me just give you an example of what we can do with it before I close by going back to enumerative geometry. Turns out that, and also work done here by Renat, that for the example that we're looking at, the mirror of local P2, there's actually an alternative, or if you want, not an alternative, because the trans series in itself is not a non-perturbative definition. It's a family of non-perturbative definitions. There is actually a non-perturbative definition in the literature, which extends for, basically all toric Calabi-Yau geometries, but let's not worry about that. Let's just see what it says, again, very schematically, at the level of local P2. The mirror curve of local P2 is something that looks like that. This bold Z here is just the complex structure modulus. The definition comes from, basically, I'm not going to motivate it, I'm just going to tell you what the result is and then compare it against what we have. It's based upon quantizing the mirror curve. So I basically sort of remove this guy, I upgrade X and P to standard Heisenberg-like commutation relations. This is just standard quantum mechanical operators. And then here I have sort of a finite difference operator. And I solve the Schrödinger equation associated to this guy, and I can sort of quantize this guy if I want. It turns out that if I do that, and if I not look at the quantized mirror curve, but I look at the inverse operator of the quantized mirror curve, in L2R, in that Hilbert space, is actually trace class and positive definite, which tells us that it has an analytic spectral determinant for which there is a conjecture that you can compute. And if that's true, then there's a spectral trace expansion where all the canonical partition functions are well defined. And you can, there's hard calculations, and by Marcus Marinho and Rinat and collaborators, where these are really weird numbers that you can compute. They're numbers. So now you can match whether the trans series can reproduce these numbers or not. By the way, so before I was working with G-string and T or Z, the flat coordinate around the conifold. Now it's N and H bar. They're basically all the same. Here I'm putting basically H bar is G-string, and N and H bar relate to lambda, which is basically the flat coordinate around the conifold. But let's not worry about details. What am I doing here? So in red, for different values of N and lambda, I'm plotting the free energy. Again, this is for different values of G-string and T. Exactly as computed by this conjecture. And in black, I am plotting just the resummation of the perturbative free energy. Nothing else. So again, it could be, we could use the results of Albrecht from 10 years ago. And it matches. And you say, that's great. You're done. You don't need the one instanton. But it doesn't, it matches up to what we can see. There's a systematic difference. Numerically small, but it's still there. So the question is whether the systematic difference can be predicted by the one instanton in the trans series or not. And here's a check that it can. All right, so let me tell you. Again, we're varying H bar, we're varying N. And what are we doing? So if you see a circle, so okay, let me say first, what are we plotting? So we're plotting the difference between the exact and the resummation of the perturbative only, and compare it against the one instanton. So I told you that there was a mismatch. There is a consistent mismatch on all those points. And I'm comparing that mismatch against the one instanton. Either it matches or it doesn't. So if you see a circle, it means it matches. The colors just mean how many numerical precision we have, so let's not worry too much about that. If you see a cross, it means it doesn't match. So you say, you're just half okay. But then you say, well, not quite, because what's this line? This line is the imaginary of conifold 2. It's a Stokes line. And on a Stokes line, as I've said at the beginning, things need to change. The trans series parameter that was fixed in some particular way needs to jump. So what happens when I do that jump? I do this cross the Stokes line, I do the jump, I find matching everywhere on the other side of the Stokes line as expected, and no longer a match before. So we can see how the trans series exactly reproduces the quantization.
So how come that you have circles on the wrong side of the line?
Of course, this is all numeric, so there will always be some mismatch here and there.
Just by chance?
Just by chance. And usually they're red, so that means that you really don't have a lot of numbers. So it looks like it matches one digit. It's not really significant.
And what's the scale parameter? Because it looks like as H bar goes up,
H bar divided by pi?
Yeah, they become more green.
Yeah, this is a consequence of numerics. I don't really have an explanation why the numerics works better at high H bar.
Because you would have thought it works better at lower, and because then as you go up, it has to take into account more and more.
Not really, because H bar is 1 over GS, so.
Oh, so then maybe that does make sense.
So
because
that makes a bit sense, yes.
No, that's fine.
Okay. All right. So that's great. But here's one question, and here is work that it's not even still in progress, but it's something that we've been talking, but we still haven't done any calculations. But let me give you a question because I think it's an interesting question. For another example, local P1 cross P1, there's actually two distinct non-perturbative definitions in the literature. So there's one, which is a quantization of the mirror curve. Here is the mirror curve. You quantize it. You do the same business that you did before. Spectral expansion of Fredholm determined and you get the canonical partition functions. This is just the same thing that we've just been discussing. But there's an older thing, actually also done by Albrecht many years ago, more than the calculation of local P2, that this is also given by Chern-Simons matrix model, a two-cut matrix model associated to that lens space. So now you can have two questions, or several questions. The first one is, in what or in how much do these definitions differ? This is a question which is only associated to the definitions themselves. It has nothing to do with resurgence or trans-series. But what resurgence and trans-series seem to be telling you is that they can only differ by exponentially suppressed terms, which is the freedom that you have when you construct your trans-series. So, or let me rephrase that answer as a question. Can the same trans-series match both results? So a trans-series will have trans-series parameters. They parameterize boundary conditions. And I can actually have a lot of them because they're associated to all the different instanton actions that I can have. And before I had 3 conifolds and 1 large radius. Now I have 1 conifold, 1 warbifold, and 1 large radius. So I have different things going around. And I can turn off some of those trans-series parameters. Sorry. And turn on some others, and vice versa. And so by turning on and off, I'm expecting to be able to match between one definition and the other. And the difference will be, of course, in what I turned on and off, which means that it's exponentially suppressed contributions. And in particular, what the trans-series, if you would say that all there is to this example is these two definitions and nothing else, you could ask, what's the minimal thing that the trans-series is adding for you? It's giving me a corresponding semi-classical decoding of this definition. What's the semi-classical data that's important for this one versus this one? All right, and now I think I have like 5 minutes, but I probably don't need that much. And let's go back to the problem of the asymptotics of enumerative invariance. And here, the questions are even bigger, but let me show you anyway. I mean, we have lots of empirical data in the computer. We don't have a theory behind it. But let me tell you what the data it is that we have. So now I am in a better situation than when I started the talk, that I said, wow, how am I going to compute a large order of all these Gromov-Witten invariants for local P2? Well, now I've done that on the B model side. So I can try to extract what I've done on the B model and bring it to the A model side by just using, here's the first terms in the mirror map between complex structure and Kähler moduli. As we discussed earlier, we want to understand, again, there's a D missing there. We want to understand the growth of these enumerative invariants in genus and degree. Remember, the Gromov-Witten invariants. And something, the trans-series must be same. This is the same plot I've shown you. Nothing happens at fixed genus or degree. I only need to pick diagonal directions. Now the question is, which diagonal direction should I be picking? Along any diagonal direction, we find that there's factorial growth. But among most diagonal directions, we cannot write resurgent-looking formulae for that factorial growth. Because basically, and I'm already telling you what's going to happen next, there is a very hard to decode contribution of all instanton actions at the same time. But there are diagonal directions. I can choose A0 and A1. They depend on T, of course. They depend on where I am in moduli space. There are diagonal directions where specific contributions coming from specific sectors are very clearly visible. So here's the first thing that we find. And this is a universal result. So we tested the resolved conifold is not really a test, it's analytically solvable. We tested local P2, we tested the so-called diagonal slice of local P1 cross P1, we tested a bunch of local curves, I think P equals 2, 3, maybe 4, I can't remember. We tested Hurwitz theory, we tested a compact case with some data actually that we took from your website, if I'm not mistaken, on the mirror quintic. And we find a universal growth of Gromov-Witten invariance at that choice of the degree. So basically this sort of tells me what is this A0 and this A1 function that I had before, controlled by the Kähler instant on action that we have already seen. And you can look at this and say, wow, this is very much looking resurgent expression for the growth of these guys. Note that this is a table of numbers, right? And what I'm looking at trying to decode them out of the free energy. So they always come with this capital Q. I'm not sure I wrote before, but this is exponential of minus t. This capital Q is exponential of minus t, which is the guy which is appearing here, right? So I'm looking at the most dominant contribution inside here in some sense. And that's how it grows. And it grows with the factorial part, the instanton part. There's some sort of, this is a Gopak-Mavaff invariant for each of the geometries. It's just a number, it doesn't matter. There's a t dependence, and then there's some polynomials. Here's the polynomials. They're all the same for all these cases. And Q is basically, remember that I'm using exponential of minus t here. G is an integer. D is an integer. So Q just corrects for the fact that, t might not be 1. And I want it to be. We don't know how to explain this. I mean, we can check this formula in lots of examples. It's always the same. Don't have a reason why behind. But you could say, well, there's something wrong because all these examples, they're all not all the same, right? So they cannot all have the same growth. And of course they can't. This is along a particular slice. So the difference of these examples is because each one of them is going to have another slice where there's going to be similar behavior and will be different from example to example. Let me try to explain you exactly how. So here we're looking again at local P2, and it's not very readable, but here I'm varying degree. I'm keeping genus fixed and T fixed. And I'm just varying degree. And what I'm plotting here is the ratio between basically this quantity for different values of degree at fixed genus and T, divided by the full free energy to know where the contribution, which ones are selected, which degrees are selected that contribute the most for the factorial growth. And you see here, there's the universal behavior that all the examples have. It's controlled by the Kähler instant on action. It's something that looks like that. But there's always something else. I'm just showing you this for local P2. All the other examples are similar, of course, at a different place. And are similar. Only because we don't really have a theory behind this, if you want numerical observation, we don't know what the functions A0 and A1 are. Here's a numerical fit of what they could be. This is 1 over A1. It's pretty linear. But 1 over A0, we really have no idea what it is. So on that depressing note, let me conclude. So I hope I sort of motivated that resurgence and trend series are definitely powerful tools in string theory, new approaches towards non-perturbative constructions. And we can basically start out with perturbation theory and then construct non-perturbative completions of these observables by using resurgence. Furthermore, they seem to be providing a semi-classical decoding of non-perturbative results. If nothing else, that's already something which is, very useful for physicists that want to sort of understand what's going on. Just giving you a number, don't explain the physics behind it, sometimes it's not very useful. They seem to be a prototypical example of coequational parametric resurgence. So coequational parametric resurgence is been shown, I think, probably by De La Baère, Pham, and Dellinger, how important it was for WKB and quantum mechanics back in the 90s. Somehow the Schrödinger equation is a linear equation. Here we're dealing with some sort of nonlinear structure. So it might be the prototypical example of coequational resurgence in nonlinear systems. Of course, we found a lot, and in fact, we have lots of numerical data in that paper of the Gromov-Witten invariance, but we don't know what the precise asymptotics is. So we have lots of empirical data, we don't have a theory behind it. We might need some general classification of resurgence asymptotics, or just maybe playing with more examples, because this seems to be going on for basically anything where you can write down holomorphic anomaly equations. And hopefully this will be a systematic tool to access the full asymptotics of these Gromov-Witten invariants. Thank you very much.
Thank you. Thank you. Is there questions?
Maybe, I think this was on your page 44 or something.
Okay.
I mean, so this was no, before, and one before, and one more before. Yeah, exactly.
Okay.
Then you had, so this is, what is plotted here again?
Okay, so I'm varying moduli space, psi,
yes,
and I'm looking at the imaginary part of the instanton action, and I'm comparing what comes out of the data against the Picard-Fuchs solution. Basically.
And then you're saying at some point when you cross this large radius.
So this is basically the contribution of the constant map that kicks in.
I see.
You can, of course, normalize, and in fact, in many of the other plots we've done, we just normalize it, we just remove the constant map from all the free energies, and then we don't have to deal with it anymore.
And then in this instanton contributions, let's say for genus G, when you fix the genus, right? I mean, let's say you plot the Gromov-Witten invariants for fixed genus. Then, of course, you get always some asymptotic growth, which has to do with the value of T at the conifold, right? And so
yeah, that's the.
So this is the easy one.
Yes, that's the easy one.
Exponential.
That's the easy
one. And then you said, what I didn't understand then in your last plot, you said, now you pick a particular direction.
This one.
No, even before. So when you said, which direction exactly? You had something where D and G is related.
D and G are related linearly. So and by changing A0 and A1, I'm picking one of these diagonals. They're here, the green lines.
Yeah.
And what we see is that on an arbitrary diagonal, the growth is factorial, but it's hard to tell what is what. So we want to have some sort of semi-classical decoding, and it's hard to tell what is what because these guys are basically on top of each other.
But then you said
so we need to sort of find directions where they
but
split.
Then the thing before you said there is something universal about it because
so these guys always
no, the P's are universal, right? They occur for any model that you
yeah. These are always the same polynomials.
And then but this is for D is 2G minus 3 or something.
Yes. So this is the one that's picking up the conifold contribution.
Okay.
Yes.
I see.
You could say that it's not a big surprise because, of course, that near the conifold, the behavior will be controlled by whatever happens near the conifold.
That's right. So then there's something like that's probably due to the gap.
Yes. And in fact, the way that we compute this formula is because at the beginning we resolve conifold exactly. We kind of extract the leading terms, and then it's easy to check that it works on.
So this is basically a universality at the conifold.
Exactly.
Okay. Thanks.
So if you want this universality.
Any other questions? Can I ask one thing?
Sure.
Is it expected to have resonance for the Gromov-Witten invariants?
Well, I don't know what that would mean because resonance is associated to a free energy, and the Gromov-Witten invariants are not a free energy; they're a table of numbers, right? So, I mean, one should not think that the Gromov-Witten invariants are resurgent. That would not mean anything. I mean, what's resurgent is the free energies. So that's part of the difficulty here is that we have simple formulae for the resurgence on the B model, but then when we translate to this table of numbers, it's a little bit harder to decode, and that's sort of the decoding. I mean, we can see that certainly the resurgence of the free energies is playing a role in controlling the asymptotics, but the difficulty, and that's the reason why I think we don't still have this closed answer on this, is precisely because a table of numbers is not resurgent.
There's no other questions. Let's thank Ricardo again.
Thank you.
And I guess we go